Now we are going to start the first session of our the third day of the GIAN course on PV fuel cell microgrid, a sustainable energy solution. A very good morning to all of you. So today in my this lecture I am going to talk about the power management of PV battery supercapacitor HESS based microgrid, and this actually the power management of this PV battery based system, battery and supercapacitor based system I will be covering in two parts. So today I am going to talk about the power management of this system, and in the second part I will talk about the PV with HESS based system. So this is my content, where I am going to first talk about the PV, wind and HESS based DC microgrid, the layout what we have considered, and then actually what I tried to tell means in my today's lecture I will talk about a system where we have considered two set of means multiple renewable energy system based DC microgrid having a single storage, and how to develop that in a laboratory environment. Okay. Then its implementation, and finally I will talk about the power management of this wind battery based wind PV and battery based DC microgrid system, and finally I will conclude it. So here actually what exactly as means till now you have seen the overall microgrid and in a large scale means perspective, but today what I am trying to focus is how to develop a system from the scratch, when we are talking means from the starting from the small unit to how we will go on the step by step we will develop it in the laboratory environment. Actually we have whatever we have developed here, so that exactly I am trying to explain you, and after in the subsequent lecture I will talk about the PV based system. Here PV and wind I have considered in place of fuel cell, because we have fuel cell based system till now we have not started working, means we have just started frankly speaking. So hardware implementation is yet to be completed. So in place of fuel cell you can imagine it as a means I am explaining it with a wind based system. So this is the complete layout where the whole microgrid, DC microgrid what I am saying. So it is provided, means the layout of the system with PV, two renewable energy sources, okay, that is multiple renewable energy sources, and hybrid storage. Hybrid storage means the battery as well as the supercapacitor we have considered. This is our starting point where the whole system is given, but so you have mainly 3 sub units and having the which is supplying a DC load. Okay. So, but in my today's lecture I will talk about the PV integrated with wind and having a single storage system, how it will be implemented in a laboratory environment. So, if you will see one by one the components of it. So, PV generating unit, yesterday I explained what are the possibilities in means what are the different converters, inverters, what are the single stage, two stage, but here it is a single stage because we are talking about a DC microgrid. So first here the DC microgrid where the source and the storage and the load is connected to a common DC bus. Okay. So here the DC bus first is the fixing the DC bus voltage. So depending on your application you have to fix your bus voltage, and here we have developed a system with a why it is not this is a 48 volt system basically, and here the when we are integrating, okay. So this is a 48 volt system. The DC bus voltage we are fixing, as we are planning to supply for a low power residential application where we can supply to a residential load, okay, having the LED lamps and the bell DC fan means those small DC loads. So obviously we have started with a very low power level, but yes, when we are planning the system, we can finally after implementing you can scale up to any value of any power level. Okay. So, that mainly is I want to focus on the how to design. So, first the 2 sources and 2 storage. So, whole is it is a hybrid energy system having hybrid energy storage system also. So, the DC grid voltage is again I am telling it is LVDC. So, I am naming it as a LVDC microgrid instead of low voltage, okay, because it is fixed to the 48 volt level. Okay. And it is a upcoming means in the Indian scenario it is a this voltage level is already accepted by IEEE standard. So, that is why we have chosen this bus voltage. So, after choosing the bus voltage, then we have to choose the source and corresponding power electronic converters. So, we will start our design. So, we have 3 units here. So, PV, wind, and first what I am saying I have considered a single storage. So, that you can understand by adding the second its complementary part of it, that is the supercapacitor. We have already discussed why we are going for a hybrid energy storage system, what is the need of it. But so, first I will explain the system with a single storage, so that in my next lecture I can explain you with the hybrid energy storage system. Okay. So, here as PV, the panel solar panel we are having. So, here we are having this DC to DC converter, which is what is the need means what it is serving. It has to extract maximum power from the available solar power. So, this is doing so what should be the this DC to DC converter, that is also a part to decide. Okay. So, this DC to DC converter yesterday also I told you this can be a buck converter, boost converter, SEPIC converter, depending on your voltage level and power level you are going to handle and how for what application. So, for all this, so first I will tell we can see the system with different type of converters also. Then the PV and the wind based system. Wind system obviously you know, as we are already Sir has also explained about the wind system, but I am not going to talk much about the wind. So, wind energy we are converting the wind energy to electricity. So, what you need, the turbine is driving the generator to produce electricity. So, here we are having AC power. So, we need a AC to DC converter, then we have DC to DC. So, here this is a 2-stage system. Here also you can have a single stage, but directly having a DC to AC, but what we have used that I am explaining. So, we have a AC to DC, the rectifier, the controlled rectifier or uncontrolled it can be, and but we for simplicity we have taken a uncontrolled rectifier or directed rectifier here. Then we have used a DC to DC converter, depending on as this voltage level is very low and we are using a this voltage level high. So, we have used a buck converter here. Okay. So, this depending, so that what I want to say is when you are choosing the this power electronics converter, that is a part of the design requirement. Then you have the storage battery. So, which can solve all the purpose, but to reduce the size of the battery we are adding another storage which is having high power density compared to this battery which is having high energy density. So, it is used for supplying the power during transient operation. But in today's case I will not explain about the converter or its uses here. So, I will talk about this first. Today. Okay. So, here then whatever I told again it is shown here in the flow steps in terms of the how to execute the task
for this, for developing this wind PV assisted LVDC microgrid. I told this is a low voltage DC microgrid because I have fixed the bus voltage to a very low level. And so first step is you can, this means whether it is wind or it is PV, this is you can take with any step. Today I am saying with a wind taking first, okay, I am developing the wind energy system. Next day I can do the PV system. So here what we have initially started, we have designed and developed a wind energy conversion system, and then we have integrated with the battery. Already I have told second step. So first then we have tried to see what are the performance of this developed with a single source, single storage. Its performance evaluation is done, okay, with a normal operating condition, means the SOC of the battery is in the healthy condition, means it is in the normal operating zone, and you can so that it is not fully discharged or overcharged. Okay. So within that we have tried to develop this, then we have tried to add the power management for that wind battery system. Okay. And after developing that and evaluated that performance, we have gone for inserting a PV system to it. Okay. We have tried to develop the PV system, means PV with the corresponding DC-DC converter, which is responsible to extract maximum power. Okay. So after that, in the what I am going to explain, this will be covered in the tomorrow's lecture. So we have added a hybrid energy storage system, means with multiple energy source we have added a supercapacitor along with the battery, so which forms the hybrid energy storage system. And finally we have developed a supervisory power management scheme to operate overall system. Okay. So this is the steps, stepwise I have tried to explain, so that you can have the idea how to develop, though the power level is low, but we can do it from the starting. So next is what I want to show. First let me explain here. Here I didn't. So here, just after showing the system, here if you see, this is the power management system or power management scheme, okay, PMS, which is having two level of control. Okay. The lower level or the level 1 you can say, okay, and the higher level control. In level 1 already, or the lower level of control, already I told it regulates the DC bus voltage and the charging discharging current of the battery. Okay. And in the higher level, here just it the renewable energy and the energy storage we have. So the current sharing between this source and the storage, it will decide, and it will regulate the DC voltage tightly. So what is our DC voltage? As we have fixed it to 48 volt, it has to be regulated constant at, or it has to maintain constant at 48 volt. Okay. Then in the higher level of control, what exactly will be doing? We have to monitor the SOC of the, means protection of the system, means we have tried to show here that means many higher sophisticated power management system can be done, but in the initial stage we have tried to monitor the SOC and try to allocate the power among the available RES and the energy storage system. So when you have a single source and single storage, so power management will be done in between, means depending on the load demand. So it has to supply to the load, and if there is a excess power, the battery will store it. If there is a shortage of power, battery will supply. Okay. So because this is a standalone system, I am not talking anything about grid connected here. Try to remember that. That is another thing we have to consider, because grid connected system design will again change a little bit. So first, so this is a standalone system where we are going to do these two operations in the power management system or the scheme we have developed. So what it should be able to, what is the criteria for, means it should be able to do the power management scheme. It should be control the output power of individual RES by doing MPPT. Okay. In the lower level we are doing MPPT, but when we are doing MPPT, So obviously the bus voltage is going to fluctuate depending on the it is a PV system, depending on the irradiance. If irradiance is varying, accordingly corresponding output voltage will vary, and when you have a wind system, if the wind speed is varying, obviously the bus voltage will fluctuate. So what is the next? So when you are adding the storage to it, so the storage, the power electronics converter, you are interfacing between the storage and DC bus should be able to capable of maintaining the or regulating the DC bus voltage, along with the controlling the charging discharging current of the battery, so which will keep it healthy. Okay, you cannot means suppose whatever is the battery rating. Already I told yesterday about the sizing of the battery. So we cannot, if it is a C10 battery, we cannot exceed the beyond the charging current, the maximum current rating of the battery. Okay, so those things should be considered while designing the system. Okay, then when we are going for a grid connected, which we have not shown here, so you have to additionally regulate the voltage and frequency, for which you have to put another power electronics converter in between, okay, between the DC bus and the AC bus, okay, or the grid. So which will be responsible for to regulate the grid voltage and to maintain the voltage and frequency constant. So which we are not going to cover in this course, but in the third step we are going to see the power balance between the generation and demand, so that already I told their storage plays the role by storing it. That is the main storage, not the supercapacitor which is additionally added to supply to give the support during the transient operation. I am talking about the battery which is responsible for all modes of operation, means during the steady state as well as the transient operation. Okay, and this step also we have not considered here, that is to have optimum cost of power generation. Okay, so you can use any higher optimization techniques so to see the cost point of view, but here during sizing analysis yesterday I have shown the one optimization method by minimizing the cost of generation. Many papers if you find people have done a lot of work on this, but I am trying to keep it simple so that you can have an idea how to develop it from a scratch. So this is the importance of power management scheme. So now, okay, so first, so we have started with that step first. We have developed the wind turbine emulator in the lab, then that drives this squirrel cage induction machine operating as a self-excited induction generator. Okay. So for this self-excited case, so this capacitor bank is very much necessary to provide the reactive power requirement. Then, so we are getting a 3-phase AC voltage here, which is converted to DC using a diode bridge rectifier module. Then our work starts. We have introduced a buck converter here, which is trying to extract maximum power for different MPPT techniques. Okay, and the simplest one is the perturb and observe, P and O MPPT techniques. All of you must be aware of. Then we have tried to improve the performance of this P and O MPPT algorithm in the lab, and the system is tested with this complete wind turbine is developed, its performance is tested. So then it is driving only without doing the MPPT. We have tested the wind turbine characteristics. Then we have tried to by including this diode bridge rectifier and buck converter, we have tried to here do the MPPT. Okay, so when we are doing the MPPT, so this is here by varying the voltage of the armature voltage of the DC motor, we can vary correspondingly. So because we are modeling it with using a wind turbine model, so correspondingly we are varying the means we are giving a speed command. Correspondingly, the output voltage of the armature current of the DC motor will vary, which will emulate the field wind turbine characteristics, and will be able to, for a particular speed, will be able to extract maximum power. Okay. So that after doing that, so but when I'm getting a maximum power for a particular speed, suppose 6 meter per second wind speed, so obviously this bus voltage is fluctuating. Okay, we are not regulating. So then when we are integrating this with a battery bank, we are having a bidirectional converter which is responsible to regulate this bus voltage, to fix the bus voltage. And when that means if wind power is proportional to what? Cube of the wind velocity. So with, okay, try to understand. If you know the characteristics of wind turbine characteristics, so for each wind speed you will be having different operating points. Okay, that is the maximum operating point, and correspondingly, but it is not that you whenever the wind speed is very high, you will be able to extract more power. But is it possible? Because there is a generator, so when it reaches the generator limit, we have to stop it. So for the wind power, we have different modes of operation, means the range of operation you can say, in between the cut into, you can say cut into here actually the cutout, okay, and the rated speed. Okay, so this is between the cut into rated, you have the MPP zone of operation, and then you have to limit the power, and after cutout you have to stop it. Okay, so this is the protection zone of the wind energy conversion system, and this is the MPP zone. Okay, and then you have to stall the machine, means you have to stop it. Okay, if it is because during the storm condition, and you cannot more wind, we should not be happy that we will get maximum power. No, it's not. We have to see the protection of the system, so we have to stop it. Okay, so you can say it as a stall zone or the packing zone of the wind turbine system. So those are again in detail I am not going. Just so we are focusing on this MPP zone, and then the pitch control mode, where we are limiting the by increasing the pitch angle of the wind turbine, we are limiting the wind power to its rated value. So it what is the rated value? It depends on the turbine rated, means the generator maximum rating of the generator. Okay, so this is how we are going to implement the wind energy conversion system or wind power generation system, WPGS or WECS, whatever you want to say, you can say. So again, this is a detailed view. So there in terms of block diagram I have shown. Just if you see, this is the wind turbine emulator, where you are having it is operating as a buck converter. So we are regulating the armature voltage for a separately excited DC motor. So here by controlling this switch, we are controlling the armature current, which is giving the wind turbine characteristics. Okay, so we have modeled. So here the design steps is for developing this whole wind turbine system, okay, or wind energy conversion system. We have 3 steps. First, to develop the wind turbine emulator. Okay, here you can have different sets also instead of DC motor, but DC motor is easiest one to implement. Okay, and this but both squirrel cage motor and generator set you can have. Okay, you can have PMSM also, which can be emulated as a wind turbine. So all these things you can get in the literature, but here we have, for the simplicity, we have taken a DC motor induction generator set, which is available in our laboratory. Okay, so after developing this wind turbine emulator, then the SCIG along with the rectifier and buck converter is, after designing, we have integrated it. Okay, so this is a buck converter, which is you are just giving pulse to it to extract maximum power. Okay, and this is actually the implementation we have done with the DSpace controller, digital controller. Okay, DSpace 1104 digital controller. Okay, so after developing this whole wind turbine along with the wind energy generator, okay, and doing the MPP operation, we have tried to integrate the battery with the bidirectional converter. This is a non-isolated bidirectional converter having a single leg. So before going for the implementation, so what we have to do? We have to design all these filter parameters, okay, for this buck converter, for this bidirectional converter. So that is also a step, okay. Design of the bidirectional converter, design of the buck converter, then you can go for a simulation, then implementation, okay. So this is a year-long work, means I am saying it in a, so obviously for the time constraint I have to skip some parts. I am not going in detail of I am not touching MPPT, how we are doing MPPT, but overally MPPT is, you just understand that it is extracting maximum power. So whether it is a wind system, whether it is a PV system, whether it is a fuel cell system, okay. So I have started with wind, so then you can do the same thing for the solar, but solar the simple, it becomes simple because it is a DC to DC directly, it is giving DC, so you can have the design the DC to DC converter directly, okay. So it is much easier compared to developing a wind turbine or a wind energy conversion system, okay. So this system again, so already I told, as we have chosen, so this can be a buck converter, boost converter, okay, for the wind system. Here as it is a buck converter, correspondingly the LC parameters of the buck converter is designed. This is the standard LC, okay. We have taken the ripple current is taken to be 30%, okay, here, and the DC bus voltage ripple is 1.5%, and correspondingly the LC values for the buck converter is calculated, okay. Just a minute. So this is the only without battery. This system, this is the specification of the DC motor induction generator set. Okay. So DC motor induction generator set, and then the wind turbine we have chosen to model it inside the MATLAB. Okay, here the wind turbine is modeled, and the controller is also designed so that it can give a output so that it means you will get the PWM to control this switch, okay, the buck converter, which is operating as in a voltage control mode, means you are controlling the armature voltage, so it will give the correspondingly wind turbine characteristics, okay. And then comes the your SAG part, self-excited induction generator, where the specifications are here. And you can search all these papers, means we have several number of papers, more than 10 I think, journal as well as conference papers, where detailed design is given step by step, means you can starting from the wind turbine, wind turbine development, how to develop the wind turbine emulator, its corresponding implementation, the how the characteristics is wind turbine characteristics is varied, the corresponding results you can go through it, but I am not going in detail of those things. Then the MPPT part also we have several journals and transactions also for this wind turbine, means the MPPT operation of this SAG, okay. So here the system is implemented in the DS 1104 I told, it is a DS 1103 digital controller, okay. And the switching frequency for all the systems we have considered it as fixed it at 10 kilohertz, okay. And gradually we are also now working at 20 kilohertz also, but the switches we have we are using the IGBTs, okay. So for this system, obviously seeing this, okay, it looks very easy, but when we have the sensors, we have all these things when we are developing in the lab, and the corresponding powers means signal processing unit is also, it takes time to develop, okay. So in the laboratory session we will one example will show in detail how to calibrate the sensor and those things, okay. Just I am showing you this is the design of the bidirectional converter, which I will tell in detail in my tomorrow's class, because here I will first talk about the what is the power management. So let us just, I want to tell that the DC bus is regulated by this bidirectional converter. So first we will design this using a standard design procedure, calculating the LC parameters of this bidirectional converter, and you have, because for a corresponding, so first the sizing of the battery already yesterday I told, okay, for what type of load, how much load, 300 watt, 500 watt, 1 kilowatt, 5 kilowatt, accordingly your size of the battery will depend. And after that you are coming for this battery energy storage system, means I am talking about battery along with the converter. Okay, so this converter design is also playing a crucial role before implementation or going for. So first you have to design the converter, then you will go for a simulation. Okay, and how to regulate this DC bus voltage? For this we are using a dual loop PI controller. So where the outer loop is a VDC control loop and the inner loop is a battery current control loop. Okay, so this controller design is also another. So each step as having many sub steps. Okay, so this controller is also designed, and we have designed the controller for this corresponding KPKI values. This slide I will share so that you can know in detail also. So we are getting two pulses to control or the operation of this bidirectional converter, where when means it is operating in two modes. One is the boost mode and there is buck mode. So when it is operating as a boost mode, means the battery, suppose here we have first started with a 36 volt and we are boosting it to 48. Now we are doing at 24 volt. Okay, but boosting when, in which case it is operated in a boost mode? When discharging. Okay, that means when there is a less power generation, so the battery is supporting to supply to the load to meet the load demand. And when it is a buck mode, means it is charging, the power flow is in this direction. So this is a bidirectional power flow. Power flow, it is boost means it is discharging, and buck means it is charging. So after designing this and simulating this, we have gone for the implementation of this, and this is the corresponding sensor circuits that is developed for this wind battery system. Okay, this is the diode bridge rectifier first for the CIG. Correspondingly, the voltage current sensors are here. Okay, and its signal conditioning circuits. Okay, and we have also sets for this the filter parameters what we have calculated. So same values are placed here. Okay, so with the setup also we will show you in the last class. Okay, though we are not going to show the wind energy conversion system full operation, but hybrid energy storage system demonstration we will show. Okay, and its sensor tuning and all those things in detail. Okay, so this is the sensor accessories for this wind battery system. Then this is the overall setup. Okay, we have this DC motor SAG set. Okay, this is the excitation capacitor bank here, and correspondingly this is the, as I told, this is a DC motor operating in a separately excited mode. So we have the field supply for the DC motor, and these are the first we have done with the this lead acid battery of 3 cells we have used, 36 volt I told, and gradually now we are going for 2 sets, means having 24 volt. Okay, so this is the resistive load we are testing till now with the resistive load. Okay, and corresponding bidirectional converter, and this is the buck converter here. Initially when for very low power we have, means 200-300 watt we have tested. So we have for the buck converter we have used the MOSFET, and now we have changed it to IGBT for little higher power application. We have designed for 1 kilowatt system. Okay. So this is the displace controller, means where it is giving the ADDA, the detail of it will be explained in our tutorial class. Okay. So after developing this system, wind system, it was tested separately for MPP operation. Okay, in MPP we have first normal this P and MPP algorithm is tested. Many things are there I have to cover. So I will just come to the power management with the wind battery system. Okay, already I told it is operating in MPP mode. When the wind speed is more than the rated, we have to go for the pitch control mode, and when this off MPP mode is coming into picture, means we are having wind power, but we cannot, because if the battery is either overcharged or at deep discharge condition, we have to disconnect the battery. We cannot operate the battery further for its protection, means for the safety of the battery. We cannot overcharge it or discharge it, so that we can have a better life for the battery. Okay. So for that, in that case, it will operate in the MPP mode. So here all the sensed voltage and currents will be sensed, and then there is a PMS, the power management scheme will decide the mode. The wind system should operate at which mode depending on the condition. It will check. I will go next slide. I will explain with the flow chart also. Okay, and this is for the this wind power generation system, or the WECS also you can say. These 3 modes are there. Okay, and for battery you have either if battery is the SOC is within the safe limit, that is here we have considered the safe limit as 50 to 90%. Okay. Okay, you can also go for the lowest one, 30 to 80 also nowadays people are taking. We have also finally modified that, but when initially we started, we have kept the lower limit as 50% and higher limit as 90%. So within that, so it is regulating the bus voltage. If it is exceeding the upper limit or it is below the lower limit, then the battery has to be stopped, means we will disconnect this bidirectional converter, so battery will be kept safe. Okay, so that I will explain you with again this is the power management scheme we have developed. So in terms of the flow chart. Okay, so we are measuring all the voltage and current of the all systems, subsystems means wind and battery system. Then we have to calculate all the power, what is the load power requirement, how much load we have connected, what is the wind power, and what is the how much is battery is taking, or what is the available battery power. Okay, so first we will check the condition whether wind power is greater than the rated power of the wind system. If it is yes, then okay, we have to limit the power. We cannot operate it at under normal operating mode. So this will go to the pitch control mode. This is the generator protection mode. Okay, and here again you will check the battery first you have it is operating in the generator protection. Okay, and after checking the generator, then you will go for the battery condition, whether SOC is within the limit. Yes, then you can charge the battery with the available energy. If wind power, because wind power is more than the means equal to rated, okay, or more than rated you can say. And if it is no, it is not within the limit, means it is either upper or lower, then you have again you need to shut down. Okay, but in this normal case, normal scenario, when it is wind power is less than the rated condition and battery is within the limit. Okay, so you will check whether wind is available or not. Okay, if yes, then you can, if it is means wind power is not available, then which is the only, so battery will act as the only source, so it will discharge to supply the load. Okay, if wind power is more than the load power, yes condition, then excess power can be used to charge the battery and the wind system will operate in the MPPT mode. Similarly, if the wind power is less than load power, then battery will discharge and MPP, the wind system will operate in the MPP mode. Similar system can be developed for if you will take as a solar, if you are taking a PV system, this obviously this pitch control mode will not come into picture. Okay, the MPP mode and off MPP mode are reduced power mode you can say. Okay, so here this is the case, and then when wind power is, another case will come when wind power is more, means SOC is not within the limit, either it is overcharged or discharged, okay, and wind power is more than the load power, yes, then you don't have storage you cannot store it, okay. You have load power you have supplied, then so what extra will do, otherwise the BDC cannot be maintained constant, so you have to switch to off MPP mode, okay. So first with this, taking all this condition, when we have tried to implement it, what we have in the normal operating condition, I will just go little fast because many things are there further to cover. So here after this is wind with battery, okay. So here we have kept the load power constant 100 watt, okay. We have done at initially at a very low power level. So and the wind is the wind here the results are with varying wind speed. So till 6.5 meter per second it is giving 150 nearly 145 or 150 watt. Then wind speed is changed to 7 meter per second, which is given around 175 watt. So the excess power here it is going to, so this is the normal operating condition, first case, okay. Are you getting it or not? So excess power is stored and suddenly there is this is constant load operation. So again wind speed is changed to 6 meter per second. So there is almost it is ideal condition, means floating condition. Whatever wind power after supplying the converter losses, it is little bit of power is going to for battery charging, okay. Then after that the wind power is reduced further, okay. So now the wind power generated is less than the load demand. So what happens? Battery instead of charging, now the battery power, if you see, it is supplying to the load, okay. So and always load power is maintained, means the generation and load power is balanced, okay. Means PW, suppose it is the power generated by wind plus this equation, this here it is already written, okay, minus the battery power, and here I have not shown the loss, the converter losses will also come into picture, minus the loss should be equal to the load power, okay. And here for all this operation, if you see, the bus voltage is maintained constant. So that we have done achieved by the using the DC bus voltage regulation using that dual loop PI controller, okay. And this is the power, the results of the waveforms of the power, all the powers. This is the corresponding battery current, okay, and corresponding SOC. Here if you will see, it is between in safe limit, that is within 69 to 70%, okay. So battery is charging, then it is discharging, okay. It is clearly visible. So this is the mode 1 operation, okay. So this is also case, just a minute. Here both wind speed is changing and also load changing, okay. Correspondingly you are able to maintain the DC bus voltage constant. But during the load variation, when the load is changing, if you will see, there is no effect on the MPP, means it is extracting the same power. So load variation should not affect, when it is operating in the MPP mode, should not affect the MPP power. It should extract the maximum power, means the whatever may be the source, it is the PV or wind. With the irradiance variation, when you are varying the load, it should give track the maximum power, okay. And same is the case when there is a wind speed variation, it is also giving the maximum power, okay. So load is varying, so accordingly the battery will charge, or it is further as the load is decreasing, it is further charged, means battery is storing more, okay. So in all the cases, so batteries, here we are showing the cases, so battery is charging, okay. And correspondingly, so first here the load variation, then we are showing again wind speed variation, but it is operating in the mode 1 condition, that is the battery is within the safe operating limit and wind speed, the wind power is less than the rated value, okay. Then comes the mode 2, when that is a battery protection mode, okay. In the battery protection mode, also here we have considered the SOC is within the limit. Okay. So that's why we are able to regulate the DC bus voltage. Okay. So here we have the load power of 100 watt, and correspondingly we are limiting the wind power also. There is no change, it is limited to its 170 or 175 watt around, okay, to its rated value. So this is at a low power condition we have tested, okay, and correspondingly here battery is, as the load power, the generation is more than the load demand, so it is charging. Okay, this is the second case, means mode 2 generator protection example. But the problem comes when you are shutting down or you are disconnecting the battery when battery is either overcharged condition or deep discharge condition. So first is the case when you are operating and battery reach the SOC upper limit. Okay, so you have to disconnect the bidirectional converter. So then what will happen? Who will maintain the DC bus voltage? Now our MPP is intact, means it is operating. So the problem here is we are unable to regulate the DC bus voltage. So that's why now it should, the MPP, the PMS should switch from MPP mode to reduced power mode. Okay, first I have shown, if you can recall. So here this is the problem I have shown without reduced power mode control, where the buck converter, instead of MPP operation, it will operate in a closed loop to regulate the DC bus voltage. Okay. So this is the results where this is the deep discharge condition, it reached the 50% SOC and the bus voltage is less than 48, it is unable to maintain. Okay. So now we are switching the buck converter, the bidirectional converter is disconnected, buck converter is now from MPP mode to, it will switch to reduced power mode or off MPPT mode. Okay. So by implementing that, so this, if you will see, this is the closed loop operation of the buck converter, where also we are, so here it was operating in the MPP mode, now it is also again the similar type of controller, dual loop PI controller, where the buck converter is operated in a closed loop condition to keep the DC bus voltage constant. Okay. So correspondingly already all these things I have explained what the power management scheme is doing and how the switching mode switching is happening, and that we have very well, means we got the result correspondingly. Previously I have shown you, we are unable to, when it is reaching 90%, we are unable to regulate this bus voltage, but now due to the switching of the MPP converter to off MPP mode, it is able to regulate the DC bus voltage constant. So with this also we have one paper, one transaction, means IEEE journal. Okay, you can go to systems journal, I think. Okay, so these are a new idea we have introduced. Okay, so we are able to manage the this power balance and regulate the DC bus voltage, means considering the battery protection also. Okay. So this is the overcharging condition. Next is the deep discharge condition in both the cases. But during deep discharge condition, what happens? If it is operating at more, means wind power is more, but load is still less, so you have to go for a load setting. So this is taking, means we have done the manual load setting here, so it is taking little more time to track the DC bus voltage. Okay, so these are the some difficulties we faced while implementing the system. Okay. So this is the battery shutdown mode when you are using this off MPPT controller, means the wind energy conversion system is switching from MPP to off MPPT mode. Okay. So here you see, means I have for previous case also, the battery current is 0. It is disconnected completely. Okay. So after implementing the wind with a battery system, then we have tried to integrate the solar system to it. Okay. For solar, initially we have taken this lamp based system, so now we are using actually solar simulator, so we can go for high power and higher voltage level. So this voltage was less than 48 volts, so we have chosen a boost converter. Okay. So boost converter, and we have implemented with this MPPT is implemented using this Arduino microcontroller. Okay. So first step. Now the system is changed much. This again buck converter we have replaced. Sorry, boost converter we have replaced by a buck converter. Tomorrow I will explain the design of that. So here the converter design I have not focused. I am saying the overall power management and its operation. Okay. When you are going to add the either it is a means source if you are adding and you have a single storage, how the complexity is increasing. So you are this here buck converter, boost converter is designed, and this MPP for different irradiance condition you can do it. Okay. So normally this for PV you can go for incremental conductance, that INC method also. P and O, INC, both techniques, and its improvement also we have done by drift-free MPPT techniques. You can go through all these papers, okay, where it is given in more detail. Okay. So here after developing this so this is the complete system PV with wind, the battery. Here also we have used a 36 volt till now. After that we replace it by 24 volt. Okay. So this corresponding converter, this is the buck converter, and this is the rectifier of the wind. All same system we have added this PV system here. Okay. In the lab, in the last day you can see all these systems are available. So after integrating this PV, again we have tried to go for different operating condition. Means along with, you just see, we have added a PV system, one more generation we are adding. Okay, so how the complexity is increasing means here, if you will see, this wind plus PV power minus the system loss should be equal to the load power, or battery can be charged or discharged depending on your generation. Okay. So you are having, so solar power, we have for this testing we have started the operating the solar power at MPP mode. You can have several, means adding one condition means again many sub conditions are arising, means whether MPP means PV is operating at MPP. So whatever we did for PV wind system, same thing is applicable for PV. So the when wind is means, but when battery is not there, think this situation when battery is, you are disconnecting a battery. So what you have to do? You have two sources having a different voltage rating. You cannot put it directly in parallel. So you need, your power management scheme has to be more sophisticated. So that any one of the system has to regulate the bus voltage. So initially what we did, as we were unable to implement it properly, so we have to manually stop one and the other one should operate. Okay, but here the results I have tried to show is for only wind speed variation, irradiance variation and load variation condition, but battery is in a normal SOC condition. Okay, so to keep our life simple, because again you are increasing the condition constants, so the complexity is increasing a lot. That final thing also we have achieved, but first I want to show by increasing one source only. So again, if when you add fuel cell to it, again, so three sources you have to manage. Okay, so like that you have to think when you are going for designing and developing a power management scheme for this DC microgrid or AC microgrid or whatever means. So with a simple example I have tried to explain it. Okay, whether you are getting it or not I am not sure. After I complete you can ask questions also. So this is a different sudden means different for battery storage system for solar, and the means there is a change in load. We have tested the system under normal operating scenario means, so that's why I have not shown SOC here. Okay, only battery current, corresponding power, all power, and the VDC is regulated. Okay, so load current also I have not shown because we are assuming that everything is means battery is under a safe limit. Okay, so SOC of the battery we are not shown here. So only the power balance is happening after meeting the losses of the system, that I have tried to show. So here initially in the case 1, the at a standard STC condition, okay, we have the irradiation is 380 watt per meter square, and correspondingly means the PV is operating only PV. Okay, then you have added battery. So then after, so till PV is operating, okay, you just see till PV is operating, the bus voltage is not constant, it is only operating at 10 pp, and when you are introducing the battery to it, it is regulating the bus voltage at 48 volt. Okay, so after that, so we are including the wind power to it. Okay, so once DC bus voltage is regulated, then we are adding another source. So you can do the reverse way, you can start the wind, then you can introduce the battery, regulate the DC bus, okay, then you can introduce the PV. Okay, so but while when the system are increasing, and in the practical scenario when you are implementing it, it is quite difficult. Okay, to so many sensors we have, so many everything we have to check properly, so for the final implementation. So here this is the system, both the generating units are, it is given, it is operating at 10 pp, load power is kept constant. So whatever extra power is used to charge the battery, and the bus voltage is maintained constant. Okay, so this is the after introduction of means we have two sources and one storage which is regulating the DC bus. Okay, then in the fourth case, the wind power is constant, the PV power is also constant, but there is a change in load. Okay, so correspondingly, but whatever, whether it is load change, irradiation change, or the wind speed change, the bus voltage is capable to maintain constant, which is done by the lower level of control. First I told, okay, VDC regulation. Okay, and the power management, you can see the example means after meeting the load demand, the PV power, the generated power is equal to the battery power plus the load power. Okay, so as the load is increasing, so you just see battery's power is decreasing. So for all this type of condition, this is then change in wind condition, wind speed is reduced. Okay, correspondingly wind speed is reduced, correspondingly battery charging current is reduced, but the bus voltage is maintained constant. Okay, so for all type of such conditions, so 8 conditions we have tried to show here. So this is that is the wind speed change condition, this is a change in irradiance where the irradiance is reduced. Okay, you just see irradiance is reduced, power is reducing. Okay, but with the load change, MPP power is not getting affected. Whether it is a wind system or this PV system, the load change is not affecting the MPP power extraction. Okay, but correspondingly your battery and storage power is changing. Okay, so to keep the DC bus voltage constant. So this is the here, then we have tried to see the system whether it is capable, means we want to make the system reliable. So without PV also the system is operating or not. Okay, PV wind is there, load is there, battery is there, PV means power. So suppose night condition, at night there is no sun, so but our system is operating well. Okay, here you see the battery power is changing, because here this one this is the load power, this is the wind power, and you are switching off the, you are disconnecting the solar system. With the no sun also it is operating. And this is the, you have disconnected the solar, you have disconnected the wind also, but still the battery is sufficient enough to supply to the load. Okay, so the battery sizing is done such that it is capable of handling the load demand. Okay, so with this I can conclude my today's session. Okay, if you have any question you can ask. So this is what we have means what we have seen. We have developed, we have designed and developed a wind power system. Then we have added PV to it. Both the PV and wind are operating at MPP condition. Okay, and the DC bus is maintained. Well, one extra thing we have added is under when there is the battery protection as well as the wind system protection. Okay, that is a pitch control mode and MPP off MPPT mode or the reduced power mode also. These two words are same. You are whatever available power, we are not operating at that, we are operating at reduced condition or off, not MPPT, off MPPT. Okay, so these are the already I discussed and it is summarized in this last slide, and these are the references, some of the references, because there are means I will put this is 4-5 pages. Some references I have shown here, and you can go through my Google Scholar and you can check more than 10 papers are on 10 or 15 you can say. Okay, and if you have any doubt now also, if you are not getting any question later also, you can contact me. Okay, and in our tutorial session I will show you the in physically the systems I have shown as a photograph. The systems are available, you can check it there. Okay, so any question? Online participants also you can ask.
Hello, ma'am.
Yeah, tell me.
When you are building experimental lab, are you designing and
yeah, please,
assembling?
Yeah, your voice is not clear. Can you repeat?
When you are building up the setup, experimental setup in your lab,
yes,
for all these to make up a DC grid, then are you purchasing the modules as such from the market, or you are purchasing the components in the assembling and then preparing the control unit for that? In this way you are building up the unit?
No, we are not. Machine obviously we are, I mean it was available in the lab. Okay, then PV panels obviously we have purchased, but the converter and the other system, the sensors we have developed individually, each unit.
Okay. Right. That's great. Okay. Yes. Thank you so much, ma'am.
Yeah, you can in the tutorial session you can see the life of it. Will show at least one demonstration, because this is a 5-6 years of work. Means I have shown a part of it, so a lot of things are there. I have not explained the means wind turbine emulator itself is requires one or more than 1 hour to discuss in detail. So that's why I told you to just go through all the papers. Any doubt, any means individual implementation is also given in detail. Okay, any doubt also you can contact me directly anytime, not during this course only. Okay, I am available to, means I will be happy to explain, because actually we have spent lot of time to develop all these things.
Yes, in the previous course also I have seen this experimental setup. In one of the tutorial the demonstration was given by one such scholar. So that's that you are building up your lab in a very nice way, which helps not only the PE students but also the research students. Research students are good.
Yes. BTechs are also working, and with BTechs also we are able to have journals also. Means last months, though the number is less, but people are, those students those who are taking interest, we are supporting them. And I am really interested for this experimental. Only simulation means I am not satisfied with that. Obviously, simulation is needed. Without simulation, we cannot go for hardware.
Thank you so much.
Okay, thank you. So I think we can close the session. Thank you all.
Okay, Namaskar, good morning to everyone. We are just going to start. My apology for a little bit late. So, in today's lecture 23-24, we will be talking about the solar resources, insolation on collecting surface, tracking system. Okay. And thereafter, we will have the PV system modeling, electrical and material characteristics of the photovoltaic system. Okay. 25th and 26th. Then a combined slide for 2 sessions, 27 to 30. It is basically an overall photovoltaic system covering the different aspects of the grid connected and isolated PV system. Okay, so I believe that if you sincerely attend this session, you will be quite good expert, quite good knowledge about the photovoltaic system. Okay, so you can check how much is your knowledge now. Okay, how much will be your knowledge at 5:30 p.m. in the evening. Okay, so you will find a lot difference. Okay, no one will be giving this statement like this. Okay, but as you see that university teaching is different than the school teaching, right? So I will just mentoring you. I will just referring. I cannot go teaching line by line. Okay, so here first of all, all the material, most of the material taken from this lecture is from the book GM Masters. Please note down GM Master. Title is Renewable and Efficient Electric Power System. I repeat again, GM Masters, Renewable and Efficient Electric Power System. It is IEEE Press, year I think 2003. Okay, so please you can Google it and you should be able to download it. Anyone want to download now? Please you can download this book. It's very useful book. Okay, even if you are teaching any renewable course, so this book you'll find, in my opinion, like among the best book. Okay, so from that 2003 version, and then it's one new version came in 2013. So some improvement, but not significant, not something drastic change. Okay, steady state change. So still 2003 version holds quite good. Of course, some of the information data you can find little bit old, but still technical information doesn't change. Basic equations remain same. Okay, so from that perspective, this book is very good. So from that book, what I am going to cover, chapter 4 is solar resources, chapter 5 is material and electrical characteristics, and chapter 6 is 6 or 7 is on the photovoltaic system. Okay, so here I am just going to start. Broadly, I will try to cover this material. Okay, as far as I can cover. Most of the important points I will try to touch upon. You will see that it will be more than what I am supposed to cover in my session. Okay, so here this first session is talking about the solar resources. Okay, like the input to the PV panels, sun rays, at what angle you will be placing the PV panel. So all these resources you are going to learn from this chapter. Okay, so this chapter you will find very complicated mathematical equations. Okay, so neither you need not to memorize these equations. but you basically understand that. Okay. If you want to just, online test, if you have to refer, you can just use them. You have some basic idea. Okay. You need not to memorize this. Okay. Even you try to memorize, you cannot, because equations are really very difficult. Okay. And you need not to feel unnecessary tense or precise that this is too complex. You have to just little bit understand and see that. When you are watching movie, just relax and watch it. Okay. So, but it is very interesting. You will find this information really very interesting. If you have to calculate how much is the distance of Earth to Sun, so you will have formula you can calculate. Okay. So the chapter is really very interesting. Okay. So here what we are going to cover: solar radiation, Earth's orbit, altitude, angle, different angles we are going to talk. Altitude angle, declination angle, solar position at any time of the day, sun path diagram for shading analysis, and then how much insolation is falling on the PV panel. Okay, so three parts are there. One is the direct beam radiation, and then you have the diffuse radiation and reflected radiation. Okay, so mostly it is direct, around 85%, then 10% say coming from the diffuse, 5% coming from the say reflected. I'm giving the approximate value. Okay, so these 10%, 5%, these are also very important. So we are going to see and understand that as well. And then finally, we talk about the tracking system. Okay, so this is what we are going to cover. So as I mentioned yesterday as well, this statement, most of the material coming directly from the book I mentioned. Okay, so here, as I mentioned yesterday, Earth received power from the sun, Earth surface 1.2 into 10 raised to power 8 gigawatt. If you can just tap this whole power from the sun for 1 hour, it will be sufficient for the whole world for 1 year. Okay, so you can see that how much is the potential from the sun. Okay, I try to relate it little bit spiritually. Okay, like you see, like all these Hindu people will know that we call it like 5 tattvas: Jal, Prithvi, Agni, Vayu, Akash. Right? So what we have exploited mainly like earth, taking coal out from the earth, generating electricity from water, like that. Okay. So, but we have not exploited the other tattvas like air and the energy from sun. Right? So, energy from sun, okay, solar, or the energy from air, wind. Okay. So, these are naturally very clean and sustainable. I am trying to present little bit different way. Okay. I just want to tell you what is there in the book. What is little bit my thought, how I am going to relate it. Okay. So basically now it is a time to exploit out of these 5 tattvas, like we had coal, unnecessarily, extracting too much. Okay. For example, we have cow, we are taking the milk, that is good, but not killing. So basically what I am trying to say that earth, if whatever useful we can do, but not damaging. Okay, so this is very important. So like earth, same way, water, not polluting water. If we pollute, then it will have bad effect ultimately on us. Okay. So whatever we have exploited, mainly that, and lot of pollution, now basically, in a balanced way. All these 5 tattvas, like we try to have, something in a balanced way. So now it is a time to have more from the solar and wind. So here you will see, interestingly, the other forms of the energy like wind, hydro. I'm not expert in the area, but I am just trying to, cope up. So you'll agree that whatever we study in the physics or science, wind, hydro, wave power, etc., directly or indirectly depend upon the sun. Okay. So, and you have seen that this, of course, we talked in the first lecture as well. So, how convenient it is to generate the electricity. It is most convenient form of generation of electricity. Do you agree or not? Okay. It is the most convenient. How much convenient? Like as you go in the market for buying of vegetable, right? If you see some person selling PV panel, you have PV panel instead of vegetable, just install it. In half an hour, electricity will start generating. Am I right or not? So it is the most convenient and simple way of generation. So and so many advantages it has. Non-noise at all, completely environment friendly. I showed you the picture first day, how much pollution it will be there, almost no pollution. Fuel cost is free, no fuel cost. Okay. Overall cost, previously it used to be costly, but now cost is no more an issue. Okay. So all these positive points are there. The only one issue little bit we have, that in the night no sunshine, and during the day little bit weather is not good, then no power generation. But otherwise it is generating power which is clean. Little bit issue of the low efficiency, but hopefully efficiency will improve further, and as we are not using fuel, so it is not that a big concern. Okay. So now basically you will see that when we are designing a photovoltaic system, so design of PV system where you are going to install, it is basically a particular place, particular location. How much, like the weather, how is the weather? So different places weather will be different. What you have weather here, weather in Srinagar will be different, weather in Tamil Nadu will be different. Okay. So the design of PV system relies on careful assessment of solar radiation at a particular site. Okay. So sun will emit as an average of energy flux of 1377 watt per meter square just outside the Earth's surface. So the total, please try to understand little bit some of the technical terms. Total power falling from the sun on the unit area is called as the irradiance. So some of the names, like we call it irradiance, radiance, sun rays, all these terms similar. Okay. So when solar radiation enters our surface, a part of the energy, like when the solar radiation will enter in the Earth's surface to inside reaching the Earth. So as you see in the atmosphere, we have the dust. Okay. So will not get the whole sunshine. Okay. Part of that will be absorbed by the air molecules. So here we are going to see again the 3 important points I told you, how the sunshine will be finally falling on the PV panels. Okay. So here you can see that in the figure that the radiation which reaches the surface directly is called as the beam or direct radiation. Okay, some of the technical term please try to understand. So whatever this, the radiation reaching directly on the surface, earth surface, we call as the beam. Okay, some of the radiation may reach to the surface reflected from the ground. So this some of the rays reaches on the ground and then say reflected on the PV system, called as the albedo. The total radiation consisting of these elements is called as the global. I will explain this again. Again, this will come at later part. Okay. So now here, the amount of radiation which reaches the ground is widely variable because of the daily and yearly variation due to the motion of sun, irregular variation caused by the climatic condition, cloud, etc. So you will not have the consistent radiation throughout the year. Okay, it is obvious. So for this reason, the design of PV system refers on the input measure data close to the site. Okay, you need to have this some data information. Okay, so another one technical term which is used, a concept which characterizes the effect of clear atmosphere on sunlight is called as the air mass ratio. So whenever you are doing calculation, one term will come AM. AM stands for the air mass ratio. Okay. So here, what is this air mass ratio? You can see this figure as well. So here, on a clear day at sea level, the radiation from the sun at zenith, just like say, perpendicular, it is 1 air mass ratio. Okay. So as an average, how much ratio is considered as an average in calculation? So air mass ratio of 1.5 is assumed as the air mass ratio at the earth surface. Okay. So here you can see H1. Here H1 is the path length through the atmosphere with the sun, perpendicular. Okay. Directly overhead. H2 is the path length through the atmosphere to reach on the surface. You can see H1 and H2. From this you can find this angle beta. Okay. So this beta is your H2 by H1, which will be 1 by sine beta. Okay. So this is what we call as the air mass ratio. I will not go into too much of these details, but once I little bit explain, you can understand it very well. Okay. Now, and honestly telling, I am not expert in this area. I am just giving you very general idea. Okay. Once I tell you, you want to build up, you can build up upon that. Okay. So here, as you know, the Earth orbit, how the Earth moves around the sun, how much is the Earth distance. So you'll find very interesting information. So how much is we would have studied long back in physics, but we do not recall every time. Do you agree? Okay. So here you'll see that at different different days of the year, so distance is different. Okay. So for example, when we have this winter solstice, 21st December, the distance from distance of Earth from Sun is 147 million kilometer. When we have this summer solstice, June 21st, this distance is 152 million kilometer. Okay. Then on the vernal equinox, March 21st, and here it is autumnal equinox, September 21st. Okay. So here the tilt of the Earth surface, the tilt of the Earth's spin axis with respect to the ecliptic plane is what causes the season. As you know that how we have the different season, so it is because of that. So Earth moves round the Sun in an elliptical orbit, making one revolution in around 365 days. Okay. So here this formula very interesting. Okay. So using this formula, D is equal to 1.5 into 10 raised to power 8, 1 plus 0.017, 360 in bracket n minus 93 divided by 365. Okay. Here you need not to worry at this stage from where this formula came, how you are going to derive that. Okay. You need not to go into too much of deeper to know each and every formula unless you are doing PhD around this topic, right? So you are the application user. So using this formula, here you will see in this equation only variable quantity is, and this formula is very simple. Here n is simply number of days. Okay. If we have today, like say for example, say 10th January, so n will be simply 10. If you have 10 March, what will be n? January 31, February 28 or 29, and January 10. So using n is very simple. You substitute the value of n, you will be able to get the distance of the Earth to Sun. Did you know this formula? Okay. So you will be like the Jyotsi. You know the Jyotsi? Do you know Jyotsi? So you can tell, okay, today how much is the distance of the Sun from Earth. Interesting or not interesting? Yes? Please say yes or no. Yes? Okay, so that's why I told this thing going to be very, very interesting. Right? So then another angle, what you see here, this angle, what you see here, angle delta. So this angle is called as the declination angle delta. Okay. So here, as we know, as we study, Earth moves around the Sun. Okay. That is what we study in science. Okay. Now here, assuming that one is stationary, one is rotating, you can consider that say Earth is stationary and Sun is doing moment. Okay, just for your reference that it becomes easy to analyze. In science we can assume anything, no harm in that, right? So you will see that on the different days, like say June 21st and this June, December 22nd. So this angle delta, declination angle delta, it has maximum value which is 23.5. 0.45. Okay. Why all this angle we are doing? At the angle, at the end, what you are going to see, how much angle you are going to place your PV panel. Okay. All this complicated thing, why you are trying to learn so many angles? Story is simple, that at what angle you are going to place the PV panel. Okay. So the angle formed between the plane of equator and a line drawn from the center of the sun to the center of earth is called as the solar declination angle delta. How you can calculate this angle delta given by this formula. This delta is equal to, this chapter is 7 from that book I asked you to download. In that book, it is, this angle is given here, and in this variable quantities again n is same what I told you. So you can easily calculate, and this maximum value of this angle delta will be 23.45. It will be June 21st and December 21st. Okay. So you can do this as well. Then there comes another angle, altitude angle beta n. Okay. So here I am not going into too much of detail, otherwise your and my battery will be unnecessarily exhausted. Okay. So here you can see same way there is angle called as this beta n. We are aware of this, what we call as the latitude. We are not going into unnecessarily too much of details of doing these calculations. So you can see here that altitude angle beta given by this equation, 90 minus L plus delta. L is the latitude and delta is the declination angle. Okay. And then from here you can find tilt angle. So at what angle you are going to place the PV panel. So tilt angle will be 90 minus beta n. Okay. Now what is the greatness of this book I mentioned? You can find so many books, okay, on renewable energy. So here the great part of that book is that it contains lot of solved and unsolved problems. Okay, it contains each chapter 10-15 solved, 10-15 unsolved problems. So you can have sufficient practice. So I will not go because of the time constraint, but I encourage you as per your convenience, if you are interested knowing this PV system quite in detail. If a lecturer you have to teach, so this is in my opinion very good material. Okay. And the example created are not just arbitrary that you have any value, just make the example. So this you will find it quite practical. Okay. This book written by the US author, as you know, northern hemisphere, southern hemisphere. Okay. So that difference you have to just keep in mind. Everyone aware of the northern hemisphere, southern hemisphere, right? So how things changes, so you have to be mindful about that. Okay. So another interesting point, you can see that if you want to know the position of the sun at any time of the day, you want to track the position of the sun at any time of the day. So what you need to know? You need to know the altitude angle beta, and then there is another angle, azimuth angle of the sun called as the phi s. Okay. So this value of the beta and phi s will depend upon the another angles called the latitude, the day number and time of the day. Okay. So this azimuth angle, phi s, the convention. What is the convention? That this angle will be positive in the morning when sun is in the east, and this angle will be negative in the evening when sun is in the west. So now you can do the calculations using these two equations, sin beta, then sin phi s. So all these angles you can do the calculation. Then there is another angle called as our angle H. So here this angle is that, as we know, that Earth rotates 360 degree in 24 hours. Okay, so 360 divided by 24 rotation per hour. How much? 360 divided by 24, 15 degree. Okay, so in 1 hour rotation is 15. 3 hours 45. Okay, so this is called as our angle. Okay, accordingly, if you have at 11 a.m. solar time H15, okay, so Earth needs to rotate 1 more hour. Okay, at 2 p.m. considering midday, so 2 p.m. is 2 hours, and after 12 it is minus. Okay, before 12 a.m. positive, p.m. negative. Okay, this is our angle. Okay, so all these numericals are given. I'm not going into that detail, but it is self-explanatory. All these calculations you can easily do that. Then another interesting point in PV system design, you are going to consider about the sun path diagram because of the shading analysis. So as we know that the shading is a problem for the PV system. We have to avoid the shading. If you have any tall building, trees, so you have to be careful, you have to be mindful that shading does not occur on the PV panel. Okay, you have to have some prediction where you are going to install PV. See, any big hotel is not going to come, which will cause the shading. Okay, so all these things you have to keep in mind. So this way we will have the shading analysis, shading diagram throughout the year. Okay, and then wherever we have our office or wherever we are going to have our PV system mounted, and then we are going to see nearby big trees or some tall buildings are going to come, and then you just see that any time of the day throughout the year that shading does not occur on the PV system. Okay, so this is the meaning of the sun path diagram. Okay, particularly when you are planning for, say, some big system. Okay, even for the small system, it is very important to have this understanding of that. Okay, so is it clear, please? Excellent. Now basically this slide, as I explained, the beam, albedo, global. So here it is very clearly explained in this slide. Okay, so here you will see that this is your collector, means PV panel. Collector means PV panel. From sun, like you have this, like the direct rays coming on the collector. So it rise this I stand for insolation level. Okay, I was teaching this course someplace, they were not expert, so I said insolation. Then someone said, is it insulation? I said, no, it is not insulation. Insulation is different. It is insolation. So we have to pronounce correctly. Okay, so that people don't get confused. Okay, so it is insolation, not insulation. Clear? So here I is the insolation, B stand for beam, direct. Okay, C stand for collector. Collector means PV panel, which collects the sun rays. Okay, so this is the IBC. Clear for everyone? So direct beam coming on the PV panel, IBC. Then you will see that sun rays will be falling on this nearby area, could be floor, any glass window. From there, it will be reflected on this PV panel. Sometime when you are sitting in the room, you will see sunrise, sun is rays coming inside the room, then see from where it is getting reflected. Okay, so this term same way, IRC. So here IB, I is the insolation, R stand for reflected, C is again for the collector. Here the sun rays going into the clouds, from the cloud it could be diffused, indirect. So this is called as the IDC. Okay, most of the insolation is direct 85%, but then around 15% coming from both diffuse and reflected. So when you are dealing the analysis, having the knowledge of this is very important. Okay, so here basically you see that now whatever we talked that on the Earth's surface we have this solar constant, how much insolation is there on their surface, 1377, right? So then we are going to see how much we are able to receive on the PV panel. Okay, so again some sort of calculations we are going to do that. You will find some little bit complicated equations, but once you practice and once you get an idea, then it's not that difficult as well. Okay, so here basically I say that starting point for clear sky radiation calculation, I naught from sun passes perpendicularly through the imaginary surface outside the Earth's surface. I naught can be written as SC. SC is the solar constant, which is 1377 watt per meter square. N is the day number, so you can find I naught. This I naught you can find. Okay. Then how much is the beam? So beam you can calculate from this relation, IB is equal to A into e raised to power minus km, where IB is the beam portion of the radiation that reaches the Earth's surface. A is the apparent extraterrestrial flux. K is the optical length. M is the air mass ratio. M or AM is the air mass ratio. So using these two equations, as I told you, this chapter full of formulas, full of equations. You need not to memorize. If needed, you have to just use. Okay. At the end, I am going to tell you, even you can have your small Excel program. You can feed all these in Excel program, and then within few minutes you give input and you can get the final insolation at a place. Okay, as simple as that. Okay, so A is given by this relation. Interestingly, you will find that all these depends upon n. N is the day number. So you have the value of A, you have the value of K. So A, K, air mass ratio is N. So this way you can find the I, B. Okay. Then, you know, optical depth K, either you can use those relations, those formulas I told you in previous slide, or you can have some data for a particular place, and from there you will have this table. You can know from this table the value of A, C and K. So depending upon this, like the day or month, you can get these values. Okay, and you can also use the formula. So both will come very close. Both will come very close. So this example, try to explain same story. Okay, so you can find the value of A and K using the formula, and you can also use the table, so the value will come very close. I'm going fine or fast? Okay, because I'm teaching more than the university students, PhD faculty, more than that. Okay, so I am just mentoring. I'm not teaching line by line, correct? Okay. Now, solar insolation on a collecting surface. At the end, you want to know how much insolation is coming on the PV panel. So here it is reasonably accurate to calculate the clear sky direct beam insulation. Direct beam insulation you can calculate quite accurately, but it is very difficult to exactly calculate the diffuse and reflected, but if it is little bit approximate, that's also fine. Okay, so it is basically kind of a bonus. Okay, bonus you cannot exactly calculate. Salary you can exactly calculate. How much you will get bonus, it will decide by the government. Even you cannot calculate exactly how much will be your DA. It depends on government, sometime 2%, sometime 4%. There is no formula that you will know. Can you predict? Difficult, right? You cannot calculate bonus, you cannot calculate DA. So what beam you can calculate, you cannot calculate very correctly diffuse or reflection, but it is a bonus. So how much more you can get it is good, right? But it is very important to know about that. Okay, bonus is 1 month salary. In some public sector, it could be 2 months salary, which is good saving, right? So you cannot neglect that, right? Very important. Mostly saving from there. I'm just trying to make the things not very boring. That's why I little bit introduce. So here you'll see that the diffuse radiation is assumed to be coming from all direction. So angle does not matter. Diffuse comes from all directions, so angle doesn't matter. Its value could be typically from 6 to 14%. Here whatever is written in the textbook, it is exactly coming from as it is. Okay, so no addition, no correction from my side. Okay, then reflected is basically surface in front of PV panel. Okay, how shiny is the surface, accordingly you will have reflection, it will be changing. So this surface reflectance rho, depending upon the surface shining. The value could be 0.8 higher side, and lower side it could be 0.1. So this reflectance will be depend upon the surface. Now we talked about the IB beam. So beam may not fall a perpendicular to that. Then we will be beam is the then we will be interested that beam falling on the collector. Okay, so I have to see this term little bit carefully. So IBC is the beam falling on the collector. So it is given by IB into cos theta. I'm not going into these equations too much in detail. Then again, whatever the cos theta, it is explained. It also depends upon several other angles. So given by this equation 7.26. And then all these calculations you have to find for IBC, making use of all these formulas, you can do. You will be able to do it. If you are required to do, you can self-study. Yes or no? Agree? Okay. So that's why if I had dedicated 5 days only solar, I would have done most of the problem. But here, half day difficult. Okay. And no need. Okay. If it is bachelor class, bachelor photovoltaic, I would have done that. But for more than PhD, very difficult. Okay. So diffuse radiation, diffuse just coming from the dust and then diffuse from there. So diffuse radiation on the collector is difficult to estimate accurately. Incoming radiation can be scattered from atmosphere particles and moisture and can be reflected by the clouds. Some is reflected to the surface, re-reflected, okay, reflected, re-reflected. So how much accurately you will calculate? So difficult, exactly. So basically, how you are going to make an estimate about this diffuse? So IDH, I stand for insolation, D stand for diffuse, S stand for the horizontal surface. So that will be C into IB. IB is the beam, C is the sky diffuse factor. So these monthly values of C also in this next table are given there. You can calculate, you can also calculate from the table, or you can also calculate the value of C from this equation 7.28, and then that value of C you substitute and you can get this I diffuse on the horizontal surface. Then please keep in mind that this diffuse is going on the horizontal surface. From that diffuse you have to see how much will be the diffuse on the collector surface. So from whatever you had on the horizontal surface, like the diffuse coming from all the directions, you can see the diffuse. So this will be IDC will be IDH 1 plus cos sigma. This 1 plus cos sigma by 2, or CIB, this IDH is CIB 1 plus cos sigma by 2. So this is how you calculate the diffuse on the collector. The calculations are given. So that's the great part of the book, that any formula, anything you are doing, you can do the calculations, you can do some calculation, you can have confidence that whatever you understood is correct and you are understanding. Okay. Then talking about the reflected, this reflection can provide a considerable boost in performance, as for example on the bright day in front of snow or water, in front of collector. It can be modest. For example, if you have some glasses nearby collector, so this reflection can be improved. Okay, so reflected radiation, the amount of reflected reflection can be modeled as a product of the total horizontal radiation IBH plus diffuse times the ground reflectance. So here reflected IRC you can calculate using this equation 7.30. Now whatever you have done, you see how much complicated formulas you have seen. If all the formulas you allow to come in your mind will become very hot, right? Do you agree or not? Yeah? Then you need tea, coffee, or like that. Okay. So whatever formulas you have got, you need not to allow to come in your mind, but you just make the Excel sheet. So please, the book I mentioned in the 2003 version, by the way, anyone downloaded? On and off student, anyone downloaded? Please download that and tell me that yes, I have done. At least one or two I really want. Okay. So in old version, this slide is not there. Okay. In new version, this is introduced. So all these you are seeing the different stuff on this part, like the some input you will be giving that which is needed in almost all the formulas, like the day number, latitude, collector surface, collector tilt angle, hour angle, all these input you are giving here. All this input information you are giving, you have developed your formula, you have placed this formula in the Excel sheet. Okay. Then after giving you input, you can calculate all this calculation, beam, IDC reflected, and then finally whatever you are seeing, my cursor please, insolation IC, you can calculate, it gives you value, for example, for this case 823. The three different part I explained you. IBC you are getting 697, IDC diffuse you get 88, IRC reflected you get 38. So total of 3 you get as the insolation level 823 watt per meter square. Okay. So whatever calculations I told you, for any place you have to do, for any place you have to do all these calculations. You will not have a textbook and you apply formula, the whole day will go. Okay. You make one small Excel program, just give the few input value, just in a 2 minute or 1 minute, you will get this. So is it easy or difficult? Easy, eh? So basically we application engineer, like download app, just put the input and get it, right? So but we as the engineer know that what is happening. Okay. Any application engineer, not necessarily to be an engineer, anyone can do that, but engineer will know in the background what is happening. Other disciplined person will not know what is happening in the background. So this is the difference between the engineer and other person. Okay. So this is very good, and in the new book this has been explained. In the old version you will not find that. Okay. So we completed one part about this input condition. Now we are just going to talk the another part, what is the tracking system. You know that most of the place we have the fixed mounted panel. You decide the whatever these different calculations were there, you see at the end how much angle you are going to place it depending upon the latitude. Okay. Now you see that if some of the PV panels can we have the tracking system. Okay. As we know, if it is tracking, it can have more energy generated. Okay. But at the same time, you will see that when we are making this tracking arrangement, movement of the PV panel, so it will need the motor, it will need the device, sensors, it is going to add the cost as well. Okay. So here the tracking system could be single axis tracking or dual axis tracking. So here basically on some of the residential have fixed mount, but sometime tracking system can be the cost effective. So tracking system could be single axis tracking or it could be two axis tracking system. For tracking single axis 20%, two axis 25 to 30%. Some of the companies who are making this tracking system, they will say, okay, please have this tracking system with us. Then you will obviously ask how much energy more I will get. They will say 50%, right? So you will know how much is the truth. So basically how much additional you can get. It says that 20% from this single and 25 to 30% from the two axis. Okay. Then again, you know, whatever these three calculation we did for the beam, diffuse and reflectance. Okay. When we are using the tracking system, there will be some change in the angles because you are tracking the sun position. Accordingly, whatever the equation you do, there will be some change, and because of that it will deliver you more energy. So let us see that calculating the beam plus diffuse insolation on two axes is quite straightforward. The beam radiation on the collector is full insolation normal to the rays. Calculated using these equations, the diffuse and reflected are found using these equations. I am not going into the detail. Here in this new book, you can see that whatever the formula we used in the previous case without tracking, what formula we had, IBC was equal to IB into cos theta. Okay. So here when we are tracking, so this is the case for the two axis. If you are for the single axis, you will have the different equations. Okay. So how these equations for the two axes, how this equation will be modified, these are given here. So you can see that this is a one two axis tracking system. Angular relations are given. Same way you can have this like the single axis tracking. So there are four different ways to do the single axis tracking. So this part is added in the new book. Okay. Whatever you will see some pictures. So this picture, what I asked you to download in that book, you will not see that. Okay. So here you can see the single axis tracking. So there could be four possible options. Single axis tracking, how the PV panel can rotate. So you can see one is here horizontal north to south. Okay, you can have this horizontal east to west, or you can have this rotation about the vertical axis, rotation about the vertical axis, or you can have rotation about the polar axis. So single axis, you can have this for this different tracking system, and then accordingly you do some calculations to get how much insolation you can get it. Okay, so I am not going into very much detail of that, but for one axis polar mount, one of the case, what will be the relations? So these will be the relations for calculation of the beam, diffuse and reflected insolation. And then this, in the new book, it gives you the relations for all the four cases. Okay, so this part is expanded in the new version of the book. Okay, now this example just try to explain you, like, you know, if you have single axis tracking system, you have the two axis tracking system, even you could have the fixed mounting, how much additional insolation level you can get using the tracking system. So I am not going into very much detail of that, but all this calculation you will find straightforward. In previous case, do you recall that the total insolation level what we had been getting in the previous case? If you recall that Excel sheet, if the value are same, so you can see how much is the total insolation, 823. You are seeing here that total insolation is 823 for the fixed mounting system. Okay, so if you use the one axis, if you use the tracking system, it gives you IBC 879, okay, and then diffuse 115, even the reflected it is neglected. So single axis, it is one axis, it gives you 994 watt per meter square. Sorry, that was the case for maybe two axis, and for the single axis you calculate for the beam and this diffuse, even you can do the calculation for the reflected as well. Okay, so two axis it was 994, without axis it was 823, two axis 994, single axis 910. Okay, so you can see the difference, how much additional insolation level you can get with the tracking system. Okay, so this chapter talking about the solar resources. Okay, so here in this chapter what we have learned, you know, background about the earth rotation system, different angles. Okay, and then based on the different angles we have the knowledge that how this insolation is falling. It is not only the beam, but it is the reflected or diffuse. Okay, how we do the calculation, then of course about the tracking. So this is the book I mentioned. It is same. The first version was 2003, then the the original version 2003, 3 or 4, and this is the second. So it is published by GM Masters, okay, 2013. It's very interesting to mention. What you think that this professor, GM Master, is from which discipline? Electrical, mechanical, civil? Which discipline? Is not electrical. Okay. Is I think from, you will check the cover or somewhere. So it is from the environmental or civil engineering. Okay. But has done the, in my opinion, great job, better than the electrical engineers. I have to be fair and honest from my perspective, right? Okay. Then this some of the material prepared by the another professor. So I am the user for that. I have not prepared all the PowerPoint myself. I have to acknowledge, I have to give the credit, right? As you are writing paper, everything is not written by you. Something contributed by others, so try to acknowledge everyone. Okay. Then, of course, we edited one book, Handbook of Renewable Energy Technology. So in that also one chapter was contributed by this Professor Keith on solar energy calculation. So this chapter gives you little bit additional information. So these are the reference. So I completed this chapter. I'm happy to take few questions. If you have, please, you have got any question, any comments from this chapter. At the end, you give the feedback. Okay. So feel free to tell how you like the chapter. Did your knowledge was enhanced? Yes or no? Did you saw some new terminology? Can you calculate the distance of Earth from the Sun with some formula? Yes or no? So it is great learning. Yes or no? So you can know the position of the Sun throughout the day. So this is great learning. Okay. 3 different ways of this insolation. So this chapter is like the very good knowledgeable. A lot of complicated formulas, but in practical implementation, not a problem. Just develop the small Excel program. When you can write the codes in Python, machine learning, so many high techs. So Excel is not very difficult. It will be difficult like for me, but not for the young guys. Okay, so any questions, any comments? Please ask anything you have. If no, then we quickly, in 2 minutes, we will have another just start. Maybe briefly how much we can cover, because we will have little bit time constraint. So I will briefly introduce. I think it is fine. I introduce and stop in between. We have about 15-20 minutes, so I think we do that. Okay. शुरू करें? Okay, good afternoon. Now we are starting this lecture 25 and 26. It is chapter 8 from the book I mentioned, GM Masters. So in the book, title is Electrical and Material Characteristic of the Photovoltaic Systems. If you have the book I mentioned, you can correct me. So it means I have read it little bit, yes. So we are going to speak. I will not go into too much of detail, but the main points I will explain. So again, you will find this whole material very interesting. So you can see how PV panel would look like. I'm sure that everyone have seen the PV panels. Okay, that is a different thing, that how closely you have seen, whether you have touched the PV panel or not. Power electronics guy would have touched it, or they have dealt with that. The people like me, I keep some safe distance. So what we are going to learn from this chapter. So what is this PV panel comprising of the cell? Okay, so what is the equivalent circuit of the cell? Then from the PV cell, we are going to build up the PV module, what we call the one PV panel module, and then after several modules, we call it the arrays. Okay, so from cells to the module to the arrays. Then when we are saying that this PV panel has this much of power output, this much of efficiency, so we want to test the PV panel under the standard test conditions, in the field conditions. Okay, as we place the PV panel in the field condition, its performance, its power output significantly drops. Okay, so we are going to see how much is the drop in the power output in the actual field condition. Okay, and then we are going to see the shading impact on the IV characteristics of the PV system. So here, very quickly, I will just go on few points. Physics, you have studied what are these solar cell. So what is the solar cell in picture? You will see that, one small square box, you will see that it is one cell. Okay, so this way you can see in the panel you have the 36 or 72 cells. Okay, so cells are basically diodes. Okay, cells are basically diodes, and diode, as you know, is comprising of the PN material. From that simple knowledge, we know that this PV material comprising of the silicon or germanium and comprising of the semiconductor material. When these PV materials placed in the sun, so sunlight is converted into the electricity. And then some of these terms like the band gap for the silicon is of the order of 1.12 electron volts, means that electron needs to acquire that much of energy to jump into the conduction band. Okay, so a little bit you can see about the diode comprising of P and N type material. As you see, when it is in the forward bias, the diode current is there, but if you connect the diode in the reverse bias, current flow is just like the leakage current. Okay, so this is the symbol for the diode, and here this is the diode characteristic. So this part, diode characteristic in the forward direction, and this is the current, diode current, represented by this no load, means the current in the reverse direction. So current in the forward direction, you can see this is very important equations. You can please take a note of this equation. So ID is equal to I naught e raised to power 38.9 in bracket Vd minus 1. Okay. So from this you can write this equation in to find the diode current, and by rearranging you can also calculate the value of Vd, voltage across the diode. So both quantities ID and Vd you can calculate from this equation. ID you are calculating from this equation. How you will find Vd? Vd will be, first you say ID by I naught, then this term inside the bracket it has got the E term. Okay. How you are going to replace E? You take the natural log on both sides. So here it becomes natural log ID by I naught. Here these terms E just gets removed. It becomes 38.9 Vd minus 1, and then you divide by 38.9, and then 1 you take on the other side, you get the Vd. So it is very simple. Okay. So here these equations given, in fact original equation is Q Vd by Kt. When you substitute all these values, it gives you 38.9. Then you see that for the diode you can do the calculation for this diode voltage. Even the current could be changing in the diode. For example, if you have the diode current say 1 amps, how much voltage you get? 0.532. Okay. Even if the diode current increase significantly 10 amps, still the voltage you get is not much different. Okay. The voltage is higher but not significantly, as you have current here significantly changed. Okay. So here the cell, as we say, is less like a comprising of the same semiconductor material. So you can say that you have got this one PV cell. So it is, you can just like the model, just like say a diode. Okay. So how you model? You have got a current source in parallel with the diode, and then you are connecting a load, and you can find how much is this current. You have got this current ISC, ideal source current ISC, then diode current and this current. Of course, any current you can apply at this junction KCL. Okay. So obviously ISC is equal to ID plus I. Okay. And this current ISC, this current is proportional to the sunlight or insolation. If insolation is more, this current will be more. If insolation drops by 50%, this current will drop to 50%. If there is no insolation, completely dark, so 0. Okay, it is proportional. Okay, so you can have this simple circuit model analysis. I am not going to the detail. It is same explanatory equation. I will be equal to ISC minus I naught, and the value of diode current you are placing from this equation I already mentioned you. And if you substitute this I is equal to 0, I is equal to 0, I is equal to 0 means this is open circuit. Okay. So this open circuit voltage, if you substitute I is equal to 0, so you can calculate open circuit voltage. Okay. And then for any value of ISC, insolation level, we can calculate the relationship between this shell terminal voltage and current, what we call as the IV characteristics. IV characteristic of the cell or PV system. So this IV characteristic of the PV system is very important. Okay. Now you have this IV characteristics of the PV cell. Okay. So how we are getting? So basically, what does it say? That if you have this diode current, okay, this characteristics. So how you are going to see, like this curve, you just bring it down. You just bring it down, and this current you just shift by your ISC. Okay. So what you are doing? First you bringing it just from up to the down, this curve. Okay. And then this part you just, because this is the current almost say dark. So if there is insolation level, whatever insolation level is there, you just make it up. So this is how you are getting this curve. Okay, this part you bring it from up to the down, and you just lifted this corresponding to IS. Is it clear for everyone? Okay. Now you will not have like one IV characteristic, but depending upon the change of the insolation level, this can become 50% here, if dark here. So you can have number of IV characteristics for the PV system. So it says that you can see that you can have the number of IV characteristics. So here you will see that even if this current is changing significantly, the change in this voltage, it will be very little. It will be very little. So again, the equations I mentioned you will be doing same way, and this equations relations mentioned here. You see that when you have IC is 4 amps, here ISC is 2 amps, just insolation 50%. But you see that change in the, even the insulation dropped 50%, but the value of the open circuit voltage, in one case it was 0.627, other case 0.61. So the open circuit voltage does not change significantly. Okay. Now this simple model, what we consider that cell with like the diode, it is not the like say very accurate representation or very realistic model, because thing is that, for example, we have got the cell. Okay, if cell will contribute the current, okay, any cell you have, the cell you place in your watch, obviously you connect in the circuit, it will cause the current. Okay, but when we are talking about the solar cell, insulation falling, proportional current will be proportional. If no current falling, means completely shaded, completely dark, zero current. Okay, so in principle it should be theoretically zero. That's the bad part of the shading, but the situation is not that problematic that it will be completely dark. So here it means that whatever model we considered, if one cell you make it dark, okay, then how much will be the current in the circuit? ISC, this is dark, the diode you connect in the opposite direction, so this current becomes almost zero. Okay, so that's the issue with what we call as the shading, but the situation is not as that problematic. Okay, so here when we are talking about the little bit more realistic model, so what we do, we consider there are several models proposed in the literature. Researchers are keep on working to develop more and more accurate model for this PV system. So here fairly accurate model you can consider that you have a small resistance RS in series and one parallel resistance, large parallel resistance in parallel. So in that case you can get a model for the cell, that a diode in parallel with a large resistance Rp in parallel, and then of course you will add one series. But just to analyze the circuit like this, very step by step. Okay, first we consider only parallel resistance, then you want to find this current. Simple circuit you can analyze. Okay, so all these slides very nicely explain this current I will be, this current I you can see will be ISC minus ID. This current will be VD, because in parallel voltage is VD divided by RP. So it is self-explanatory. Now in second case you consider, say if you have this resistance then again you want to find the diode voltage. It will be your voltage V plus I RS. All these calculations you will see in the circuit, very simple. But when you are considering both RP and RS together, then you want to find how much is the current in the load, how much is the voltage across the load. So current, you can see this current I will be ISC minus ID minus this current. So this current will be VD divided by RP. This is the current in the circuit. How much will be this voltage V? So it will be whatever you have the voltage VD here or here minus I into RS voltage drop here. So this is very simplest circuit to analyze. Okay. So whatever you had the original IV characteristics, when you are considering this little bit more accurate model, so there will be little bit deviation in that curve. So you can see that because of the parallel resistance, the current will drop delta I, which is equal to V by RP in the parallel resistance, and there will be drop because of the series resistance. The drop delta V will be equal to I into RS. You can see the effect when this delta I drop is there. So whatever you have this curve, it will be little bit drop by this way. So the slope will be 1 by RP. And how you will consider the drop? Delta V, which is equal to IRS. So it will have this drop, delta V is equal to IRS. Okay, so here we studied the basics of the diode. From the diode we compared that it is like a cell is just like the diode. We started with the very simple diode model, then we little bit modified, and we can see how these IV characteristics get modified. So you can see in this a PV panel, in the simple language PV panel, you see this one square, it is one cell. Okay, so here you see how much voltage generally it will contribute, 0.5 volt. Okay, so this voltage is not any practical value, okay, for electricity generation. Okay, so obviously we have to connect number of cells in series and parallel to get the respectable voltage. 18, 36, whatever voltage you want to get, accordingly you have panels, number of cells are connected in series and parallel. So from this cell you call it PV panel, or you have the module. Even this module has got the say power output say 150 watt, which is also not something significant. Again you need the several panels even to meet the one house requirement. So you to get the required power, required voltage, required current, you connect the this number of PV modules, panels in series and parallel, and then that forms from simple cell to the module, this module, and number of module, it makes the arrays. Okay, so you can see here cell to the module, and module to the array. So please give me little bit time, 10-15 minutes, so that I can complete this chapter, okay, rather than breaking and then restart it. So I'll please give me some time so that I can complete this. So you have, for example, a 36 cell. It could be like 36 cell, or it could be 72. So 36, each can have like say 0.5 volts. Theoretically it should give you 18 volts, but there are resistance, etc. So typically you get the 12 volts. If it is 72 cell, it gives you voltage 24. Okay. Then all these simple equations, calculations shown here, resistance, all these calculations, you can do that. These are very simple and straightforward. So in fact, PV system, the calculations are really very simple. All these are like the DC circuit. The calculations are very simple and easy. Okay. Now here, for example, this spreads slide, very important, very interesting. From here, the concept of MPPT, maximum power point, it will start. Okay. So for example, whatever the voltage you saw, the diode voltage, say around 0.5 volt. Okay. Then you have this current from these equations. How much is the module depending upon the number of cells? Okay. How much is the power? Power is basically your current in the cell multiplied by the voltage. Okay. So if you little bit increase and decrease the voltage, say normal value is 0.5, you say 0.49, you do all these calculations. Then if you increase the VD little bit, 0.51, 0.52, etc. So, and then you get this current. Interestingly, current, all these calculations, based on the calculation you do the current. Then you have this voltage and then power. So interestingly, you'll see that you'll find there is only one point where you will get the maximum power. Okay, only one point where you have get this maximum power. So that is called as the MPP point. So here, as you are doing this, like module, you are having the different number of modules you are connecting in series. Okay, so considering this simple circuit, say you are connecting 5, 10 or n number of modules in series. So this slide very nicely explains you. Maybe now or please later, as per your convenience, try to understand, try to practice. Okay, so then really you can have very well understanding. I'm not saying that just in 2 days, but whenever you have time, whenever you want, so you do a little bit practice, you really understand these things very nicely. Okay. Then same way, all these, what you had, that this IV characteristic for the N cell. If you had like one cell, it will like this. Okay. So depending upon how many cells are there, accordingly, it will have like these different curves. So finally, with the N cell, you have this current. You see, in series circuit, current will be same. Okay. So whether you have one or N, current will be this. Okay. How the voltage will build up? 1, 2, up to N voltage build up on this axis. Okay. Then same way we are talking about the module with only parallel. Okay, how this effect is there. We are doing that modules with parallel only cell model, like when we consider only this resistance, parallel resistance, how we are doing all these calculations. So simple and straightforward. I'm not just repeating, but when you have this parallel resistance, you show how this curve will drop. Okay, this is for one cell, and for n cell the curve is like that. So a generic model, that how we are representing the cell, a parallel resistance, then a series resistance across each. Okay, so if you are representing the model and then you are doing the calculation, do you find it difficult or easy? Fine. Okay, do I need to explain more? No, I think, because this is very simple and you can learn very easily. Okay, now basically here it will come the concept little bit what you call as the fill factor and cell efficiency. You have got this IV characteristic of the PV panel. In this, how much maximum size of the rectangle you can fit in that. Okay, so here that will be your fill factor, and accordingly you can find the fill factor, the area, this area divided by this total is like say your cell efficiency. So here basically when you have this PV panel, PV module, you want to test the PV system. Okay, so when you want to test the PV system, there will be some standard condition on which you want to test. So this standard condition is called as the STC. So it is not a short course or like that, it is standard test condition, STC. So what are the standard test condition? We consider here insolation level of 1 kilowatt per meter square, air mass ratio of 1.5, and nominal temperature temperature of 25 degree. This is the ambient temperature, atmosphere ambient temperature, not the cell temperature. Okay, so these are the standard test conditions. So when we have to compare the performance of the different PV modules from the different manufacturers, so we will test them under the some standard test condition. Okay, now as we said that we expect that temperature should be around nominal one, but too much variations. Winter we can have 5 degree, 10 degree. Summer it can go nominal temperature around 50 degree. So how it affects the output power from the PV system? Common person will have thinking that if there is more, summer, it will produce more power, but it is not the case. Okay, so in hot locations, it is not the PV panel which will drop the efficiency. Even human being will drop the efficiency. Too much sweat, cannot focus for study. Right? Too much cold, difficult as well. Okay, we need ambient condition. Okay, so here basically with this, how the voltage and current affected, you see that the open circuit voltage will drop 0.37% per degree centigrade for crystalline silicon, while current increases by 0.05 per degree, and overall power decreases by 0.5% per degree. So these points for the crystalline is very important. You can have note down and please you can use. Then cell temperature. First we talk about the ambient temperature. The cell temperature can be 25 to 30 degree above your ambient temperature. You have the ambient temperature, then cell temperature can be 25 to 30 degree higher. So in hot summer 35, here hot summer could be close to 50. Okay. So how much will be the cell output? So this cell temperature, how you will calculate the cell temperature? T ambient plus NOCT minus 20 divided by 0.8 into S. S is the solar constant. So this example explains you very well. I will quickly go through this example. So here you can see that impact of cell temperature on PV module. We have a PV module of 150 watt. Under conditions, one sun insolation, ambient temperature of 30 degree. The module has NOCT of 47 degree. Okay. From this we find the cell temperature using this relation. Ambient temperature is given 30, NOCT is given 47 minus 20 divided by 0.8 into one sun insolation. So it gives you us the cell temperature of 64. So how the VOC and current will change, as it says that for module at standard temperature of 25, VOC for this table, for this module at standard temperature of 25, VOC is this. Since VOC will drop 0.37% per degree centigrade above 25, so this voltage from 42.8 it will drop. This is the equations. So 42.8 in bracket 1 minus 0.0037 in bracket 64 minus 25, it gives you voltage of this 36.7. And so your Pmax you get like your 150, what you had the nominal rating 150, so it will decrease by 1 minus 0.005, 64 minus 25, so the power output will drop from 150 to 121 just because of the one variation of the temperature. So you can clearly see the effect of temperature. एक टेम्परेचर की वेरी करने से 20% पावर रिड्यूस हो गई. Okay, now let us see the impact of shading. Okay, so as you see that when there is shading, it has significant effect. Power output could be dropped by 50%, even if a portion is shaded. Okay, so basically, when you have the PV solar cell model you have seen, so when this cell is shaded, it means that it is not contributing any current. Okay, it means that becomes open circuit. So when you want to do the analysis, so here you can see that because of the shading, this is open circuit, and moreover you have many cells in series parallel. Say if one cell is shaded, okay, or few cells in a PV module are shading. So you are going to analysis that obviously they do not contribute to the current. Whatever you have this current in circuit, the another bad issue what you have seen, this is not contributing, but this is causing the voltage drop because the parallel resistance is high. So if it is not contributing the current, okay, some person in the team, if someone is not contributing, it is okay to some extent. But if the person is causing the further disturbance, you will see how much is the problem. अगर एक आदमी काम नहीं कर रहा कोई बात नहीं, अगर टांग खिंचाई कर रहा है तो देखिए कितनी दिक्कत होगी. तो this is what it is happening here. It is having the not contributing plus causing the problem as well, voltage drop. So you can see this simple analysis. The additional points, the figure drawn are very simple, straightforward to analyze. So you can see that because of the shading of the cell, the voltage drop delta V, this amount you can get it given by this equation. We can see, like when shading is there, what could be the solution, to avoid the shading problem. So one solution could be to provide the diode across each cell. So diode across each cell will not be very practical because it becomes very complicated. Voltage is dropped. So basically what it can be done, this is example. You can see that analysis of this circuit. What you see, how much the example we are continuing from 8.4 with some data. The voltage was 19.41. If one of the cell is shaded, even assuming that current remains the same, so what will be the new module output voltage and power? What would be the voltage across the shaded cell? How much power will be dissipated in the solar cell? So see, because of the shading of one cell, the voltage drop will be 14.66. Then how much will be the new voltage? New voltage will be 19.41 minus 14.66. So how much voltage you get? 4.75 instead of 19.41. There is significant voltage drop. How much power output you will get from the module? Assuming that current rate is the same, current could also drop. So this module output will drop to 10.1. It was expected to deliver 41.5. It drops to 10. Just like the 25% you are getting, 75% is just gone because of the shading of one cell. Okay. In the same situation, if the student is done very wrong, okay, in principle lecturer should give the 0, but lecturer is little bit considerable, so at least give 1 or 2 marks or 25%. Even for the wrong, they will say at least something should be correct. Okay, so same story here, theoretically 0, but at least you are getting 25%. So this is really one of the big problem of the shading. So see how this shading can be avoided, shading diagram, all these things, shading, be considerable as far as possible. So all this calculation given here. Now we talked about that, if you connect the one diode across each cell, not practicable. What we can do, we can place one diode across each string, one series circuit, we can place one diode. The another issue sometime with the shading, what we see, that if you have got, say for example, some strings in the parallel, if one of the rows got shaded, okay, so current is being contributed by other rows, so whatever is shaded they are not contributing. So what it can happen, that the current flowing in the load, the current can start flowing in this shaded portion, circulating current. So this can be another issue. So to avoid this problem, what it can be done, that for each string you place one diode in the reverse direction, so it will avoid the flow of current in the reverse direction. Okay, so this we completed. I thought that rather than breaking in between, we just continue. So this was the chapter 8 from the book I mentioned, electrical and material characteristics of the photovoltaic system. Here we show the model of the PV systems, starting from the basic concept of the diode. Then we move to, develop the realistic model using the RP and RS. Then we show the effect of the temperature, how the power drops, and then we saw the shading problem, how we can avoid the shading. So all these basic stuffs we have learned. So I just stop here. References more or less stay same, what we saw in previous chapter. So we are just going to stop for the lunch, and please, if you have any queries, question, you are more than welcome. If there are no questions, we'll stop about an hour. So please try to be a little bit fast for the lunch, about 1 hour, and we can try to meet and try to complete according to the schedule. Thank you all for your kind cooperation. Thank you all. So I'll just stop. Then we are going to mainly discuss from the chapter 9 of the book I mentioned. Okay. So in the chapter 9 it says the photovoltaic systems includes both isolated and grid connected modes, various issues of that. So here in lecture 27 and 8 you can see some part have been discussed in the previous slides, like impact of temperature, insolation, effect on the IV curves, we saw that, but we are going to discuss like the MPPT, and then you can see that in the next lecture 29 and 30, what we are going to discuss, stand-alone photovoltaic systems, estimating the load, how we are going to estimate the load for the stand-alone photovoltaic systems, battery storage sizing, optimal sizing of renewable energy sources in microgrid application, capacity factors, PV connected grid systems, and its economics. So this we are going to discuss based on the chapter 9 of the book I mentioned, and these are like in one session. So here basically what are the contents we are going to discuss. The development in the PV technology, we discussed, renewable energy integration, we gave the nice overview, and then some part already we discussed, like some standard test conditions, etc. Then we talk about this photovoltaic system. Some part we find a little bit repeated. We will quickly go through it. Then when we have these IV curves for photovoltaic system, then what are the other components like the loads? So loads could be different types. Resistive load, it can be DC motor load. We have the battery storage system, and then we talk about these IV curves, the MPPT trackers. Then we talk about the grid connected system, interfacing with the utility, capacity factor for grid connected system, grid connected system sizing. If you want to decide what should be the size of PV systems, how we are going to decide, we will discuss. Then standalone system, batteries, battery storage capacity, battery sizing, blocking diodes. We talked about the blocking diodes in previous topic as well. Then how we decide the sizing of PV system for standalone microgrid or standalone PV system. And then we briefly touch upon some issues. Of course, we have done this in the very first day as well. So this is what we are going to discuss. So we expect to complete this in 1 or 1 hour 30 minutes, depends upon how we move forward. Okay. So if we see the development of PV installations, so initially PV systems have been small size, okay, and like the distributed. Then around year 2010, until 2010, majority of PV systems were connected small size distribution level. In recent year, because of the drop in the cost, we have started talking about the large photovoltaic system. And if the power rating for the PV systems is significantly higher, and then obviously we will be connecting them at higher voltage level depending upon the size. PV system integration in the sub-transmission or transmission system. So this slide a little bit old. In this first part, I showed you that by end of 2023, we already have more than 1,600 gigawatt of the installed capacity worldwide from photovoltaic system. You can see the trend that mainly you can see PV system started integrating around 2008, 2009. But thereafter you can see how exponentially growth of the PV system is there. Particularly in the last 4 or 5 years, you can see how exponentially this PV installed capacity worldwide is growing. So if you see the cumulative growth rate in photovoltaic systems worldwide, 2016 say until 2022, so this growth rate has been like 32%, lower side 23. So if you take as an average 25%, so within a period of 4 years, the installed capacity worldwide, it will just become double. In fact, as the cost comes little bit more down, there will be more and more significant capacity addition. So within a period of 3 years, so the installed capacity can be doubled as well. So as such, we do not see any barrier that why we cannot have, even more than that capacity addition. Of course, whatever is the revenue needed, that has to be arranged, either government or whoever is installing. But other than that, we don't see any negative aspect from the PV system. Okay, so it has almost all positive features. Okay, so in future we can see that the capacity addition will be even faster. The cost has come down, and all things are in favorable of photovoltaic system. So this slide we already talked about that when we are integrating PV system. So at which level we should be integrating, either in the distribution or in sub-transmission or transmission. So, or at what voltage level. If we have very small size PV system, we individual house, so if the house is small, we will just connect them at the voltage 230 volts. Okay. Of course, with the application of power conditioners, inverters. But if it becomes like a large farm, I give an example that PV systems in our country we have more than 2000 megawatt capacity. If you are going to, generate 2000 megawatt power, okay, so voltage you have to go for higher level. It is the simple equations. Power is equal to voltage multiplied by current. Okay, if voltage you keep it very less, for example, you want to generate power 2 megawatt. If voltage you think that 230 volts, think of how much will be the current. Okay, same thing what it applies transmission of power through the transmission line. Okay. So if amount of power to be transmitted is significantly, significant, huge amount of power you want to transfer, then obviously you have to increase the voltage. If you don't increase the voltage, that current will be very high. If current is very high, then your transmission line conductor will be very thick. Okay, it will add more cost on the conductors, transmission towers. So basically, when we are designing the power systems, we see that two important considerations are there: voltage and current. So we should have suitable voltage, suitable current. Okay. How much current we can carry through the wires, conductors. So accordingly, we have to select the suitable size of conductor, wire size. If current is less, we will select the thinner size of conductor. If we have more current, we will go for the thicker wire. Okay, if you try to pass huge current through thin wire, it will melt down. Okay, as simple as that. Then what about the voltage? Whether voltage is low or high, accordingly we have to provide the amount of insulation. Here I am talking about the insulation, not insolation level. Okay, so insulation level, for example, if you are using the wires for 230 volts, you will have this thing. But if you have the cables, for example, 11 kilovolts, okay, so you can see how much insulation level we are using. Like these cables can be used for 11 kilowatts? Obviously no. Okay, so depending upon the voltage level, we will have the higher amount of insulation in case of cable. Even if we have this transmission conductor, overhead conductors, what we are doing, we are keeping the appropriate spacing between the conductors. Insulation is the medium. So we have to select the appropriate voltage. As I mentioned, if the power being generated is significantly higher, then we will connect in the sub-transmission or transmission system. Then when we are integrating power system, then we see some other issues. Power electronics. Power electronics means the converters. You saw the role of converters is very important in the renewables. Whether this PV system is isolated or grid connected. So role of storage system is very important. Power quality issues. When we are, having the converters, it is very much essential in the renewable energy. But when we have converters, you see some power electronic issues can be generated, harmonics, etc. So we have to be careful about that, like how we reduce the harmonics using the filters. So all these things have to be taken into consideration. What sort of issues we are going to consider when this PV system is being integrated. If it is a small system, we consider the issue like the moving clouds effects. If it is medium size, for example, if the government decides that most of the people have their own PV system, okay, government encourages, government gives the rebates that, okay, we will give you some rebate, you can have your own PV system, okay. So in that case, what could be technical issues? Okay, so as you will see that during the midday, say around 10 to 3, you will have maximum power generation from PV system. Okay, and obviously you will see that during that day, midday, in residential areas, the load will be minimum. As people go for work, children go in the school, okay, so load in the home is minimum. So generally you will see that power generation is maximum. Power generation is maximum from PV, but load is minimum. So there is difference, significant difference in the generation and demand. So that can lead to have some issues about the frequency regulation or voltage regulation. Okay, when there is significant capacity addition in localized area, so it can have some frequency and voltage regulation issues which needs to be considered. If you have large size PV plants, I explained. So with the large size PV plant, basically what we are doing here, we are essentially replacing the synchronous generators being used in power generation, coal, gas, nuclear, large hydropower plants. So these rotating generators are being replaced by the static PV generators. Okay. As you know, this rotating generator will store the kinetic energy, and that kinetic energy is used when there is sudden disturbance in the power system. Okay. If there is sudden increase in 500 megawatt load, okay, so from where this load will be suddenly met, electrical system is not going to wait. It just needs the very instant. Okay. So whatever energy stored in the as a kinetic energy in the generator, that will be used for the instant purpose, and then thereafter system tries to stabilize, and fuel input can be increased to have matching of the sudden increase in the load. So these are some of the very briefly some of the key issues we talked. We examined a PhD student, the student first say, Rakib Shah. So he studied the stability challenges for large integration of PV, large size PV integration. So he started his PhD around say 2011. When he submitted his first paper, then he got the comments from one of the reviewer that authors, what they are thinking, large size PV plants, it's just like the imagination, that even in the 2011 you will have hardly large size PV plants. Okay. So you can see how fast this PV technology has been there, that in few years you can see how much significant large size PV plants are coming up. Okay. So the first paper, you can see very nice review paper discussing about the key power system stability issues for the large scale PV integration. So this is very nice review paper, has attracted large number of citations. Then you can see some other interesting paper dealing with the stability analysis, damping performance analysis using the battery and energy storage system, ultra capacitors, shunt capacitors with large scale PV system. And then you can see that the last paper, it says that oscillatory stability analysis with high penetration of large scale photovoltaic systems. So as I mentioned, we tried, in most of the cases, we try to have target the high quality, high impact journals. So all you can say 3 papers published are in Elsewhere journal, Elsewhere Science Direct journal. So they have quite high impact factor, like renewable and sustainable energy issue. I think now this is around 16 or like that. Applied energy conversion and management. So impact factor around 9 or 10. Okay. So the very nice study done by this student. Okay. Then I already mentioned that at University of Queensland, we have initially we built up 1.2 megawatt PV system on the main campus, Thereafter, it was expanded in other campuses as well. So the total capacity was 5 megawatt. So here you can see that previously we used to have like through this link. So previously through this link in real time you can see this graph, how is the weather, how solar electricity generation is taking place. Okay. Now I'm not sure whether we can see in the real time or not. I have not tried. Then you can also see that some other information, very interesting information you can find on this website about the practical experience of the photovoltaic systems, like what type of PV systems have been used, what is the storage technology, etc. So you can get very good practical experience, learning lessons, outcome from these PV systems. So you will find a lot of interesting information, white papers on this website. Okay, so some of the slides coming repeated, but it's okay. So we are just trying to little bit revised explain you, because the topic is really very interesting. So as I said, the configurations, we can have 3 configurations. Grid connected PV system, or PV system is very small, can be mounted on the pole, or PV system can be placed on the rooftop of the building, or this PV system could be integral part of the building, what we call as the building integrated PV, BIPV. So some place, maybe if you would have visited IIT Delhi, have anyone visited? So you can see like one of the building in front of library. Have you seen anyone? Yes? You notice that roof is PV material. So it could be building integrated PV. Okay. Then we have this standalone. In standalone, we have to be more careful about the backup. So backup batteries. Then diesel generator, optional, may or may not be there depending upon the situation. So PV system, isolated configuration. We talked about the PV system, this configuration, like its application in the agriculture system. So in agriculture systems, like the country like ours, so we have huge farmers. There is need for this water for irrigation purpose. So if we have tube wells, how we are going to extract the water from the ground? So we can use this PV along with DC motor. We do not want to use the battery to have the low cost from the PV system. Even not inverters. We want to have simple system, very robust, low maintenance and least costly. Okay. So this configuration, like as the water pumping for irrigation application. So whenever we have this solar sunshine, it will run the DC motor and water we can use. So even doesn't it matter, like say moving clouds comes, so if it is stopped for half an hour, 1 hour, it's not big issue, right? Because the water we need is for irrigation purpose. Okay. So it doesn't need that we need the continuous power. So whenever it comes, it's good. Okay. So that way we want to have low cost solutions for the farming applications. In fact, one PhD student did PhD around this topic, water pumping applications based on PV. How I know I was the examiner for the thesis. So he did quite good work. Some related with more kind of practical experience, like how many water pumpings we have, some practical data. He was maybe working in some industry as well. Okay. Then we already saw the IV curve. We already saw the IV curve of the PV system. As I said, it is not only one IV curve, but there are several IV curves as the insolation level changes. Now, where we will operate our power system. Okay. So we will have load. What is the nature of load? Okay. So say this is your load curve, where the load curve and photovoltaic IV curve will be crossing each other. That is the operating point. Okay. So obviously we will be interested that operating point is closer to the neck of this IV curve. Corresponding to the neck, it is the MPP. So from here you will see the concept of maximum power point tracker. Okay. Now we little bit try to understand the components we are using in the PV systems, like the load, different type of load, then battery storage system. Okay. So here, if we have, for example, resistive load, this we can simply do experiment in the laboratory itself, very simple. So you have got PV panel, one or more, then you have got the potentiometer, rheostat, a variable resistance. So by varying the resistance, increasing, decreasing the resistance, you can change the current. Okay. So you can have the different currents depending upon how you increase or decrease the resistance. So what does it mean? That you can have this line, you can have this line, depending upon how much resistance you are making. So 1 by R here, it says the slope. Okay. So you have some flexibility where you can operate your system. If the resistance is this, you are operating here. Okay. If you have this resistance, you are operating here. Or if you have this resistance, you are operating here. So obviously our interest will be operate corresponding to this point MPP condition, which is obvious. So in general, we know that voltage is equal to current into resistance. So when we are talking about when we want to extract the maximum power from the PV, so obviously the value of this resistance corresponding to maximum power, it will be voltage, we say that Vm, current is IM. So we have this point corresponding to MPP condition. Like wherever you see neck is there, from the neck point, you have dropped this line vertically and horizontally. Vertical line is your VM, maximum voltage and maximum current. So as we talk, as insolation level changes during the day, very early morning, 10 a.m., 11 a.m., 12, 2, 3, 4, 5. So you will see that sunshine keeps on changing, insolation keeps on changing. In the early morning, we have lower insolation, say 200 watt per meter square. Okay, around 10, it can be 400. Okay, this way it will increase when we have higher insolation level, and then afternoon again it starts decreasing. Okay, so now you will see that we don't have one IV curve. Okay, we have the several IV curves, say 5, 7 IV curves, what you are seeing in this figure. So for each of the curve, you will see that where is the MPP for each curve. Like for this one, you are seeing this neck point. Here, this one. Here, this one. Here, this one. Here, this one. So basically, even MPP you want to do manually. Okay, through the resistance you can try to adjust, say corresponding to this point. Okay, but as some time changes, it will not stay corresponding to MPP point. So you have to be continuously keep on tracking the insolation level, so that we can operate our load corresponding to MPP condition. We can have maximum output from the PV system. So this MPP obviously needs to have automatic, not manual, because manual controlling not very accurate and difficult. So obviously we will have some device which it can keep on doing automatically. Okay. Now let us little bit understand the DC motor. We use, for example, irrigation PV systems for water pumping application. So its characteristic, in the starting, it will have, as we have any motor, it will have generally high current. Okay, then once motor starts, its currents will decrease. So you can say that this is a DC motor, current versus voltage IV characteristics. So here you will see that when we are using the same application, PV system for irrigation application, DC motor, now you can see that DC motor characteristics, here DC motor is the load. Okay, so this IV characteristic we superimposed on the photovoltaic IV characteristic. Okay. So for this motor to start, how much insolation level we need? For starting, it needs around 800 watt per 400, you can see starting current. So it needs the insulation level of the order of 400 watt per meter square. So say for example 400 watt per meter square, it will generate say around 10 a.m. in the morning. Okay, but we want to have the say very long duration application for water pumping application. Okay. So what we want, that if motor can somehow be started corresponding to say 200 watt per meter square level. So for example here it is 10 a.m., here it is 8 a.m. If you want to have long hour of operation for the DC motor, so how you can do that. Okay, so here basically what we are doing here, we are placing one more component called as the LCB. LCB stands for linear current booster. Linear current booster. So it can help like say MPPT condition. So the current, it can reduce the DC motor current. The motor can be started corresponding to reduced current. So you can see that if we are using this device LCB, motor can be started closer to say 8 a.m. in the morning. So motor can have the extended hours of operation. So this way linear current booster or any device similar to that can be very useful. Now we little bit understand the IV curve of the battery, as battery are very essential part for the PV systems. So energy is stored in the batteries for off-grid applications. Now what will be the IV characteristics or some important information for the battery? So battery, what sort of equations we have? Batteries. So here you can see that batteries, we have some initial resistance, then the voltage what you call as the across the terminal of the battery, and what you measure like say across the panel. So there will be some, they will properly related with the voltage drop terms. Okay, so here this voltage you can see V PV panel V will be equal to VB plus I into Ri. Ri is the say internal resistance of the battery. So you can see that IV characteristic of battery is just like say you can sort of straight line, okay, theoretically. Now changing the IV tilt line with a slope of 1 by Ri, applied voltage must be greater than VB. Discharging IV line tells to the left, tilts this discharging battery IV line tilts to the left with a scope of 1 by Ri. So you can see here what are the characteristics during charging, during discharging. So during charging they are tilted like on this, little bit on the clock, means on the right side, whereas during the discharging it is tilted slight bit on the left side. So this is IV characteristic of the battery. Now very simple example, what you are talking, you have the battery. If battery you connect to the photovoltaic panel, okay, so in that case obviously which direction current will be there, either from battery to the PV or PV to the battery. Which direction current will flow? Current has property to flow from the higher voltage to the lower voltage. So accordingly there will be an appropriate current. So here you can see in this some simple example. It says that you have a nearly depleted 12 volt lead acid battery which has open circuit voltage of 11.7, internal resistance of 0.03 ohm. What would be the PV module operation if it is delivering 6 amps to the battery? Then if 20 amp is drawn from the fully charged battery with open circuit voltage of 12.7, what voltage would the PV module operate? So very simple example, just you are using in A part the PV voltage will be, the voltage peak will be equal to VB plus RI into I, or very similar you are finding this so which is explained here. Now let us talk about the MPPT, the concept of maximum power point trackers. So it says that efficiency gain can be significantly realized if the operating point for resistive DC motor, battery, etc. Could somehow be kept near to the knee of PV IV curves throughout the ever changing daily conditions. Like as you see, insolation keeps on changing, so IV curve keeps on changing. So you want to keep the operation of the system corresponding to knee point. Okay, so when you operate the device corresponding to knee point, we call the device as the MPPT trackers, which track the position to keep the load closer to the knee point. Okay, so here in the next slide you'll see that the circuit in the next slide is combination of two circuits, and is called as the buck and boost converters. A buck and boost converter is capable of raising or lowering the DC voltage. So you can see that you have a converter, which could be buck converter, boost converter. So you have got the PV system, sources, then DC motors, and then of course in between we have the we are using the converter, so which is basically a high frequency switch, inductor, capacitor, and the diode connected in the reverse bias. So this boost converter called as the MPPT. So this MPPT, the switch we mentioned in this circuit, so this switch is not the simple switch what we are using in this our electrical systems. So this switch is a transistor or FET switch which flips on and off. It is on and off at rapid rate of the order of the 20 kilohertz, while the load is this transistor switch, my apology, this transistor switch, electronic switch based on the IGBT or FET, field effect transistor. It is electronic switch. So it flips on and off at a rapid rate, 20 kilohertz. So this is not the ordinary switch, but it flips on and off rapidly. So with this switch on and off, how much duration this switch is on, how much duration this switch is off. So from there we have the concept what we call as the duty cycle. I will show in the next slide. So you can see that how in one cycle how much duration we can keep the switch on, how much duration we keep the switch off. So this we can adjust, we can change. So we can have this on time greater than the off time, or we can have opposite to that, or both we can adjust equal. So this duty cycle can be adjusted. So what does it mean? What is its effect? So here the voltage, one side you have from the PV panel, other side you have on the load, in between you have got the converter. Okay, so you switch. So this switch, by adjusting the switch duty time, you can change the the voltage across the output. Okay, so here I'm not going into too much of the detail. Here, as you can see, the D. So here in this clearly you can see B part here, D is 0.5. half of the time the switch is on, half of the time switch is off. Then here you can see that on time is lesser than 0.5. Here it is more. So accordingly, I'm not going into this technical or long-term discussion, but the concept is very simple. You have the output voltage, input voltage. What you'll see basically how much time the switch is on, how much time the switch is off. You see in the converters, you have the inductor, you have the capacitor. So these inductor and capacitor will store the energy. You can see that here when the switch is closed. When the switch is closed, current is flowing. Switch is closed, current is flowing through this. Okay. This circuit, the diode this direction. Right? So inductor is energy stored in the stored. Then when you switch off, that whatever energy was stored during the when it is off, that energy should be dissipated. So whatever you say when the switch is on, how much is power stored, then the same should be dissipated when the switch is off. So both these power you can just make equal. And when you simplify this equation, so the ratio of output by input, simply you can relate with the only quantity D, which is output by input voltage will be D divided by 1 minus D. So here negative sign is not of very concern or important. So you can easily see the relation between the output and input voltage simply by the term D. So interestingly, for example, you can see this example that we have a PV module. Its maximum power is at Vm is equal to 17 and Im is equal to 6. What duty cycle its MPPT should have if the module is delivering power to 10 ohm resistance? So you'll see that maximum power will be maximum voltage multiplied by maximum current. So given here, maximum power will be 17 multiplied by 6, 102. So that maximum power you want to deliver to the resistance of 10 ohm. So for delivering of this maximum power to 10 ohm, again you know the relation that power you want to transfer 102 watt in the resistance 10 ohm. So you know the relation P is equal to V square by R. So it gives you this voltage across the resistance, voltage across the load as using this power 102 resistance of 10 ohm. It gives you the voltage across resistance 31.9. Okay, so you have your input voltage 17 volts. This maximum input voltage 17, maximum current 6, then maximum power 102 that you want to transfer across this load resistance. So what should be the voltage across the load, output voltage. So this voltage you saw that it is 31.9. Now duty cycle we need to find. So simply you can relate with respect of this equation. Output voltage divided by input voltage is simply equal to D divided by 1 minus D. Minus sign you can simply neglect. So it gives you the value of D is equal to 0.65. So here you will see that when we want to have output voltage higher than input voltage, then the value of D will be higher than 0.5. If you want to have output voltage lower than input voltage, then D will be lower than 0.5. Okay. So this boost, it will simply act like the MPPT because it can transfer the maximum power. So it basically explains you the concept of MPPT. So some of these things, for example, when we have the grid connected photovoltaic system. Okay. So in grid connected simple small photovoltaic system, what sort of components we have? If your small PV systems, like here in the Department of Electrical Engineering, your small PV system, you want to connect to the grid. So what sort of these components we have got? Of course, we have got the several PV panels which will be connected in series and parallel to get the required voltage, required current. Then you have basically a sort of the box, what we call this box, a combiner box. It includes like the diodes. These diodes we call it the blocking diodes for each array. Okay. And then you have got like the fuses. If there is overcurrent, so it can protect. Like here in our system we have got the MCB. So fuses. Then you can have little bit more what we call as a protective device, like say lightning surge arrestor. So this way you have a standard combiner box. Then you can have some device called as the array disconnect. If any of the array you want to disconnect, you can have the array disconnect. Then you have basically inverter, DC power being generated by the PV systems to make it AC before feeding into the grid. So you have the inverter, then you can have a breaker to connect or disconnect if needed this PV system from the grid. Okay. Then you are feeding this power. You can have grid connected system. You have this home or some load. The power produced can be utilized by the home. Excess power can be fed into the grid through the net metering scheme. If home needs more power, power can be drawn from the grid. So there is a concept of net metering. So the meter can rotate in the both directions depending upon the direction of power. So here these are the some of the components you will see in a grid connected PV system, but I explained if you have small PV systems like here, few panels, and you want to connect the grid, the components needed. If your PV systems like a very big farm, PV farm, obviously components will be more and complex. Okay. Because as we have bigger system, then we can incorporate some bigger and complex systems for protection and so many other stuff. Okay. Now the concept comes that when we are using these PV systems, how many inverters we have, whether we have, many inverters or lesser number of inverters. Okay, what is the choice? So, if for example in the previous slide I showed you, like say one inverter, or you can have several inverters of small size. Both will have some pros and cons. If you have individual small inverters, it can allow easy expansion. The connections, distribution panels are simple, need the less expensive cabling system. Or if you have a bigger system, then it can be economical, it can be less costly. Okay, like if you have say 10 small inverters, whatever capacity is there, if you have like one bigger, so obviously single bigger size inverter cost will be less. So both have got some pros and cons. Now when this PV system is interfacing with the utility, obviously there is concept of net metering. In principle, customer will pay for the amount of the energy that PV system is unable to supply. But there should be a kind of proper, what you call the MOU. Okay, if the utility agrees and they are willing to pay. If they say we don't have provision, we don't pay anything. If you wish, you can. Okay, so is not something. So and then again, it could be when you are taking from the grid, how much is the price? When you are feeding the power into the grid, it may not be at the same. Okay, so there could be difference as well, because they are managing, they have more overhead charges. Okay, so when you are buying costly. When you are feeding, you may be giving the cheap supply. Okay, even if some nominal difference is there, not a problem, but it should not be there that you are just giving for the charity purpose. Okay, at least something is there. No, when you are regularly and consistently in some significant quantity you are doing, then it cannot be free. So in the event of outage, PV system must quickly and automatically detect from the grid, as we said that renewable power system. Okay, so now renewable power points have been developed significantly. They are not immediately disconnected, but try to stay on the grid as far as feasible. So they try to help in recovering of the fault. How? Like the PV system can operate with the leading and lagging power factor, means that they can supply the reactive power. During the fault condition, generally voltage drops. Okay, so voltage, for example, if because of fault, voltage becomes 0.8 per unit. If the PV system can supply power, if it can bring the voltage again back to the 0.95 or higher, so it means things are done. So PV system need not to be disconnected. But if the voltage comes very low, it is difficult even for PV system to help. In that case, might be you have to disconnect. So it depends upon the situation. And then of course you can have some kind of backup, although in the grid connected system you have the grid as the backup. But if the grid itself is highly unreliable, okay, and your solar power is not sufficient, you should have some kind of storage system, okay, so that there is sort of backup. Now we have to understand about the DC and AC rated power. This concept really very important. As we know that DC connected system consists of an array of modules and power conditioning unit that includes inverter to convert DC power from PV system into the AC required by the grid. Okay, so basically now a good starting point to estimate the system performance is that rated DC output of an individual module under standard test condition. So standard test condition, one sun insolation. One sun insolation means 1 kilowatt per meter square. One sun insolation means 1 kilowatt per meter square. Like as we say 1 unit of electricity, it means 1 kilowatt hour. Some standard terms are there. If you say 1 unit of electricity, it means 1 kilowatt hour. So in this technical term, if you say 1 sun, it means 1 kilowatt is standard term. So AM is air mass ratio unless specified. The standard term is 1.5. Nominal temperature is 25 degree. So when a PV system is placed in the field condition, okay, so it may deviate from the standard condition. If the temperature is high, so the power output from the PV system will drop, as we have seen it. So in that case, we have to see that how much power we are going to produce. The AC power, what we are going to get from the PV system, the PV is generating DC. So you have the conversion efficiency. Okay. So this conversion efficiency, it does not only talk about the efficiency of the converters, but it includes several other factors as well. So one is of course the inverter, but what are the other points? Inverter efficiency, then if there is dust accumulated on the PV module. Okay. So how much clean? Is it like a brand new, no dust at all? Even like say how frequently you are cleaning the PV module. Okay. If too much dust, either you cleaning like 1 time a day or 2 times a day, or if it's less dusty in 3 days. So you see what is the optimal between the cost on the cleaning and like that. Okay. So you consider the some efficiency loss because of the dust accumulation. Then mismatch of the module, I will explain this term, mismatch of the module. and then difference in the ambient condition, ambient temperature. As you see that whether ambient temperature is 20 or 25 or ambient temperature is say 45. Okay. So it will have significant effect on the power produced by the PV panel. So even you have the full sun insolation 1 kilowatt per meter square. So even in the full sun, because of the impact of these losses, the power output can be less 20 to 40%. Okay. So we already saw the effect of temperature variation. Now let us try to understand what are these losses because of the mismatch. This is very interesting concept, quite nicely explained. Here you can see that it illustrates that impact of slight variation in the module IV curve. We have the PV module. It can be from different manufacturers. Okay. Once you have PV module from one manufacturer, we want to have its expansion, then maybe some other manufacturer may be available. So basically you can see that because of the some mismatching condition, for example, you can have a PV panel rating say 180 watt. PV panel rating is say 180 watt. So one manufacturer supplies the PV power of 180 watt. One is supplying at say 30 volts 6 amp. Okay. Other one is supplying at say 42 volts 5 amps. Both PV panel have the same power rating. Okay, if one manufacturer you get 180 watt, then you got from the another manufacturer again 180 watt, but both have the different voltage and current ratings. You thought that power rating is same. Sometime non-technical people will come and they will say, don't worry sir, you should worry about the power rating is same. So why you are worrying, we are here, don't worry, it will operate excellent. They will confuse the expert people as well, right? So if any salesperson comes, don't worry sir, we will give you a little bit discount as well. Okay, don't worry, it will work better than your original one, no problem. So you'll think that this person will say, please be honest and don't, I'm poor guy, please, I'm just solely dependent upon you, right? So this is how things works, Okay, don't try to cheat, please. So I leave it to you. So this is how things practically work. So you can see that this is we call that when you are matching, you not only match the power, but match for the, okay, I will take from you, match the power, match the voltage, match the current. Okay, no problem. Then you'll see that that is a proper matching. If you have the power matching, voltage and current different, it is called the mismatching. Okay, so here you can see that both PV panel 180 watt. So theoretically, you think that 180 plus 180 connected in parallel should give you 360. Okay, but when you are connected them in parallel. Okay, so basically one is like say 36, another is 42. Okay, so it may end up depending upon like say delivering you some lesser power, maybe end up with 330. For example, one PV panel is giving you 5 amps. One PV panel is giving you 5 amps. Another is giving you 6 amps. So total current becomes 11. So current is 11, and then the voltage, okay. So it will not give you certainly 360. So this is called as the mismatch. If you have mismatch, so because of this mismatch, there could be efficiency loss up to 4%. Okay, so little bit if we are not careful, so 4% gone. Okay, so just little bit careful that avoid the mismatching. So then we see that another term what we call here in other countries we call it STC, standard test condition. In US they have there's another rules, they call it PTC. So PTC stands for PV USA test condition, PTC. Very much similar but little bit difference. So here you can see that if we consider 1 kilowatt PV system under standard test condition, module, we talked about the term NOCT. What this NOCT stands for? Nominal operating cell temperature. NOCT stands for nominal operating cell temperature. So this considered as 47 degrees centigrade. So DC power output at MPP drops 0.5% per degree above the STC temperature of 25. Estimate its AC power output under PTC conditions if there is a 3% array loss due to the mismatch of the modules. Efficiency loss of 4% because of the dust, and inverter has efficiency of 90%. So here just to explain you quick concept, based on the conditions we calculated the cell temperature. So cell temperature 53.8 degree. Then based on that we calculated the power output because of the high temperature, how much power we are getting, 1 kilowatt into 1 minus the power drops 0.5%, 0.005. Temperature difference is 53.5 as we calculated here, minus standard nominal temperature, ambient temperature 25. So it gives us power 856 just because of that temperature variation from 1000 we simply come to the 856. Then different efficiency loss, whatever power we got 856, then efficiency lost because of the mismatch 3%, so 0.97, then 4% because of the dust, inverter efficiency 0.9. So overall you see it gives us 720 watt. Okay, although PV system we say that it is 1 kilowatt, keep in mind it is DC. Okay, then how much AC power you are expected to get. So what we are saying, then all these conversion efficiency loss, it is not only just inverter but some other factors, mainly the temperature variation. Okay, what it is saying 1 kilowatt, it is in the STC, like what is your efficiency in the AC room, right? When you go in the field, it drops. Okay, same is the device. So when it is the perfect condition, then it is delivering 1 kilowatt. When you take on the rooftop, 50 degree, 20% directly gone. So you can see that 30 to 40%, something like that, will be the drop in the power. So this we talked little bit about the PTC, etc. I am not going into the capacity factor, like you say that similar to what we call as the plant factor, plant load factor. What we have, for example, these conventional power plants, it can operate almost continuously. Okay, but we have constraint here, PV systems, how many days out of 24 hours, 6-7 hours. So its capacity factor is comparatively low. Okay. Now when we want to have decide the sizing of the grid connected PV system, how we'll decide the sizing that we want to have the grid connected PV system we want to use for the commercial purpose. So where we want to install this grid connected system, so we can see that how much is the space available. For example, we have the different buildings, we want to use the space of the roofs of the buildings. Okay, so we have to see how much is the space available for us where we are going to install the PV system. Then we have to see how much investment we want to do that. Okay, we have to see how much even we can have huge amount of space available, but then we have to see how much initially investment we want to do. So we have to see that how much investment we are going to do. Then of course, if we have money, if we have space, but then again we have to contact the PV utilities, how much power they want to buy. Okay, so at least how much they are willing. So we have to consider these factors, that how much space available, how much money we want to invest, how much power utility are willing to buy. So all these things we have to keep in mind. Okay, once you know that annually how much energy we are going to supply, this much energy means kilowatt hour. Okay, so this much electrical energy we are going to supply to the utility. Okay, so that energy what you are going to supply for the utility in, for example, 1 year. Okay, in year you have got the 8760 hours, but then you have to see what is the capacity factor for PV system. As an average, for example, 6 hours, 7 hours every day, then you see how many hours you can have the PV generation. You consider that. So then you calculate the kilowatt rating of PV. Keep in mind that what kilowatt you are getting is AC, and then you have appropriately conversion, and then you decide the DC rating of the PV system. Are you following? AC and DC. I gave you example in the previous slide. Then based on that, then you see to get, say for example, 100 kilowatt, and then you have to select that, say in 1 meter square area how much panels you can have, spacing, all these things you can keep the calculation. Okay. Keep in mind, when we have system very big, then we have to consider some in between spacing may be required for maintenance purpose, etc. So you have to follow the standard guidelines. Then of course, when you are selecting the components, PV panels, inverters, batteries. So again, once you did the calculations, then whatever you are going to select, obviously you will select what is there available in the market. Okay. So inverters, how many inverters, what sizes, then also make the decision what is available in the market. So here, when we are talking about the grid connected system sizing, so the design involves more around the non-technical parameters rather than technical parameters. So talking about the how much space available, how much investment capacity we have, how much is the buyer is willing. So decisions moves around these points. So this example gives you little bit calculation. I'm not going into the detail, but you can have these simple calculations that an energy efficient house to be fitted with the rooftop of PV array that will annually displace all the 3,600 kilowatt hour per year of electricity that house uses. How many kilowatt DC under standard test condition PV will be required, what area will be needed. If you have to make some assumptions, you can suitably make. So again, you see from DC power you have the AC power. So considering the appropriate number of hours operation as an average, depending upon which place you are going to install, okay, based on some data, and then you consider suitable. First we calculate this is the energy, yearly energy, okay, unit is kilowatt hour per year. Then from this we want to keep the term just like kilowatt, okay. So for hour we divided by days, and then as an average how many hours PV can generate the electricity, 6 hours, 7 hours, 5 hours, depending upon which place. So it gives you like the AC power 1.73, then DC power. So both DC and AC are related with the conversion efficiency. So you consider conversion efficiency including the efficiency of inverters around 10%, then power loss because of the temperature variation, dust accumulation, if there is little bit mismatch. So all these factors you consider, maybe conversion efficiency 30%, 20%, whatever you decide, you consider. So it gives us the DC power rating, and then based on that you can calculate for this much of power how much area will be required, knowing the size of the PV panel and considering the other space conditions. Now we talk about the standalone isolated PV system. So when we are talking about the isolated PV system, we design technically it will be more complex. Okay. So here basically one main point we have to keep for the standalone system, more concerned about the backup. Okay. What kind of backup we are going to have for the standalone PV system. So generally we have the battery, but we can have the diesel generator, which may be optional. So you have the PV system, charge controller, batteries, and then inverters. All these things we need to consider. We can have the diesel generator, maybe optional. Okay, so when we are going to design the standalone PV systems, where we are going to place, we need to know about the loads. Okay, like whether the standalone PV system is required for what application. Okay, it is for the domestic purpose, it is for some office purpose. So we need to know its occupancy, we need to know its users, okay, what kind of load is there. We need to do the calculations for the load. So for example, you need to know the power requirement for, say, typical household or maybe different types of load. How much is the power consumption? How much is the power consumption? What different types of loads you can have? For example, you can have the refrigerator. How much power it will consume? What size refrigerator? How much power it is going to consume? I could have dishwasher. Could have this for cooking purpose. If it is the gas, is fine. But if it is electric, so I have to consider its load. Then microwave, general households like the clothes, the washing machine, ceiling fan, air conditioner, heater, clocks, hair dryer, television, printer, in office printer, computer, laptops. If it is like the industry, what are the some other devices? Okay, if you some multi-story building where you are going to use this PV system, you may have the lift as well. For example, little bit big office can have three lifts, for example. Okay, so again you have to consider the diversity of the load. You know the diversity of the load. All electrical engineers know that all the connected load we are not going to use at the same time. We have the air conditioner, we have the heater, we are not going to use at the same time. The washing machine we are not going to use all times. Electric iron we are not going to use all time. So we need to have diversity, particularly when we are talking about the emergency load. For example, we have the normal supply, all the three lifts might be operating. When we have diesel generator, then just basic, one lift is operational. Okay, so all lights will not be on, just whatever minimum basic you can manage to life going on, like that. So again you have to consider the diversity. If you want to have design for a building, you are the consultant. If you have already similar building, your things becomes easy. Or if you have information, all these informations you are going to consider for the isolated system. But we show that in case of grid connected, we need not to do all this stuff, because here we are just simply selling the electricity grid connected, okay, and we just see how much we want to investment, how much is the space available, how much is someone is willing to buy. But here we have to make an estimate for the load, and then we have to consider backup. So in fact you see that isolated system requires more technical design, Okay. Then in isolated system, some of the consideration, few I discuss, few more you can see, that in standalone PV system design begins with an estimate about the load that needs to be served. We discussed this point. Then trade-off between more expensive, efficient appliances and the size of PV and battery system needed. Like we can also see that whatever the load we have got, okay, partially we can have some partially DC load. If we can partially use DC load, so it can be directly supplied from PV system. We need not to have the converters. Okay, so that point we should be considering. Now, like the backup, emergency. Okay, so as I gave you example, isolated system, like for example, several story office building. So backup generator kind of thing, that what sort of fraction of load we are going to consider for the backup. When normal supply is not there, how much load we run on the diesel? Not the full load. Okay, then the diesel generator will be too much expensive. So how much is the essential load? It is people stay in the office, manage with like the fan, not like the AC. Some basic stuff is there. So one lift working, something like that. You see what fraction overall you have. Then one more important point, for example, when we have these motor loads. Okay, so motor load, you will see that starting current of the motor load will be high. Okay, so that what we call starting current, in-rush current for the motor loads, that also needs to be considered. And then very important point, I would like to mention that what should be the sequence of connecting the loads. Okay, that how much current is PV system able to supply. Okay, so when you are connecting the load, first you connect the motor loads, because initially motor will draw the large current, you have got this space. Okay, motor starts, it takes high currents, we have capacity available, then it settles down. Then you have the static load, so that first you almost exhausted your capacity with static load, then you start the motor loads, so it will go above the rated current. So even sequence of operation is also important. So all these points needs to be considered. The list design is not exhaustive, but at least give you some basic idea. Then we are talking about the battery. In previous sessions, we have also talked about the battery. So when some topics comes again and again, it means this is really very important topic. So these batteries in PV system provide the storage, help meet the surge current requirements, provide a constant output voltage. There is lot of interest in the battery research because of these electric vehicles as well. When we are doing the need for the battery, so several points needs to be considered, like the cost, weight, number and depth of the discharge, efficiency, temperature, performance, discharge rate, charging rates. So several important points needs to be considered. So broadly, we completed this chapter. Again, some of the important reference. Mostly I talked from this book. Very important. Please, at least every student, online and offline. Offline are physical. So it is very interesting. Which are actually present, they are offline or physical. So please download this 2003 version. At least you have some resources talking about the renewable, wind, solar, very nicely explained. Some other topics are also there. And then this the paper I mentioned, something talking about some stability challenges for large scale PV integration. You can see another good review paper talking in general some of the technical issues for PV systems. Some other research paper contributed by my students, kind of review papers. You can find several research paper as well in the literature. So we are just at the end of session. I will be happy we have some time. So it is basically from my side, whatever the contents I was expected to deliver, I have delivered, but we have some time. So I think we have some time to ask again some questions. I expect maybe one question as an average from every participant. Okay. So if not, simply say, hello, how are you? So you're done, eh? So at least I want to have, later you say I attended. So even the online student, we cannot see that, but we'll try to see that if the photo can be on, we can recognize some student, or at least see if they say, I attended your course, so at least I can say, yes, I recall your face. Eh? So it is very important. So let us see, please try to just ask some question. In fact, generally I present another interesting topic, like we are all researchers, academics, either PhD student, master students, faculty members. Okay, most of us are academics. So for us, publication is extremely important, either PhD student or masters. So basically, publication, proper planning is very important. Okay, and for PhD or master student, so plan from the day one publication, because publication itself takes time. Okay, the process itself takes the time. Okay, so just see, first of all, just see what is your institute or university requirement. Okay, clearly find out what is the minimum requirement in terms of publication, what sort of publications are required, Scopus journal papers, SCI journal papers, what is the minimum requirement? Okay. So that minimum requirement should be completed. If minimum requirement is not complete, it means your thesis is ready, it can delay because of the, that requirement is not complete. Okay. So first of all, just try to complete the requirement. Then on the top of that, you can publish more. And please always try some good journal. Keep confidence in you, have proper planning, and try to go not very high, but at least some good quality publication. So this is very important. And some of the things very important, like we are aware of all the ethical issues. Okay, like in the school time, we say कि नकल नहीं करना, cheating नहीं करना. It is not good. Okay, but later when we become more senior, sometimes we forget little bit knowingly, unknowingly, ethical issues, plagiarism issues. Okay, so basically when we have a paper, it is written by researcher, faculty member, like any programming we are doing, we have the flow chart, if and then. If this yes, then we move to the next step, otherwise go back. Okay, so please keep in mind as a rule that you check the similarity before submitting any document. Okay, because sometimes student has written not by intention, but sometimes whatever reason there might be some similarity, there may be unnecessary problem. So please ensure that similarity check is done, and then basically analyze the similarity. Sometimes similarity might be coming high, but the means that it is not, we need not worry. When we go to the doctor, they say BP is high or temperature is high. So we cannot be doctor our own. Doctor will just see the reason for that. Okay. So analyzing the report is very important. Okay. So sometimes high could be because of some unnecessary issue as well. Okay. So please have check for that. Then some of the recent stuff, ChatGPT. Okay. We thought that it will be very useful. It can be very useful, but if something is used sensibly. Okay. But if you just use, order the ChatGPT, please prepare for paper for me. Okay. So like so basically that will not work. Okay. You need some assistant for something. So intelligently you can use, but we cannot be complete boss that okay, please prepare 2 paper by tomorrow for me. Right. So even when we are submitting any paper in the journal, first notice will pop up. Have you used the AI tools, ChatGPT, etc. Okay. So please be careful. Please stay ethical as much as we can, because when we are publishing, whether we will get the benefit or not, obviously we'll get it benefit. When we'll get, how much we'll get, that is the different story. But if we make some mistake, single mistake, knowingly, unknowingly, we can be in trouble. Okay. So it is always good that we are very, very careful about these things. So I know all understand, but still sometimes we mentor, we advise, so a few of the things. And so I just completed from my side. So I would like to thank you all. But please, if you have some questions, queries, please more than welcome to ask. So please, if you have some queries, questions, or we have other faculty members, so we'll see that how we are going to move forward further. Any quick questions from please, any participants? I have already given you my contacts, email, my phone numbers are there. So please, anyone is welcome to contact me. Stay connected. So I want to really thank you all for your great interest. When we are at the end of the year, most of people are having holiday. You are doing very hard work. And I want to give this, sincere thanks and their commitment, like this, all this team who are, helping this, making the material online. Okay. And so many teams members are involved, academics, students, drivers, food preparation, list is endless. Okay, I want to sincerely thank everyone for great hospitality, their great commitment. So thank you all. So it has been great for me to deliver this GIAN program. I hope you enjoyed. It met your expectation. Okay, so the learning is not completely finished. As I said that I give several reference. If you need something more, then we are stay connected. So please, I'll just stop here, and then let's see how we continue further. Thank you all. Yes, please. थोड़ा आवाज आपकी क्लियर नहीं आ रही.
सर अभी आया है सर, ठीक है. I think some problem is on my side.
बोलिए.
It's clear now. Yes, sir. Thank you very much, sir. I think today is your last class, sir. Tomorrow you have any session.
Do you hear what he said? Last session. Yeah, mine is last session. I completed, okay. But other 2 days the Professor Sarkar, Professor Pattnaik, they will be engaging these 2 days. I had some personal things, so I just wanted to little bit complete early. But I am available in online mode.
Yes.
Okay, so you can send me message online. You can talk me online.
Yes.
I will respond in real time.
Okay.
And I will be available even after 5 days as well.
Sir. Okay, sir. No problem.
So we'll have some group photo with on. Yes, sir. Yeah, we would like to have maybe some group photo with the online student as well. So we'll just, Dr. Sarkar will tell that we just to make the video on, so that we can try to have some group photos.
Hello. So now we would like to take a group photo with offline and online participants with sir is here. So I request online participants to turn on your camera so that you will be visible in our screen, and we can take the photographs. Participants can turn on their camera. Yeah. Okay.
कैमरा का ऑन हो
चेयर या सोफा जो भी कन्वीनियंट
उड़ा हाँ कैमरा का ऑन हो
So I request other online participants also to be online and be turn on your camera so that we can see you and we can take the picture.
Online, please on your camera. This will mark your attendance as well. बैठो बैठो
from side or this side we don't have idea. Hello.
speaker audio
डिस्टर्बेंस नहीं हो उसमें उसको तो एक स्क्रीन
Thank you everyone. Now the photo session is done. You can turn off your camera.
Thank you, sir. Thank you.
Thank you. So our next session will start in 15 minutes.
Energy level, sir, का अच्छा है.
Hello. Okay, so good evening to all. So online participants, can you hear me? Am I audible?
Yes, sir.
Okay, thank you. Okay, so welcome to this last lecture of today's session. So here I will discuss about the application of microgrid in EV charging system. So basically, in order to understand this, we need to understand the EV charging, the effect of EV charging, and how in microgrid the microgrid going to help us in mitigating and helping the grid to come up with some solution which can mitigate the detrimental effects of EV charging. I should not say detrimental, but it's a random nature. EV charging is random in nature. So it is not like it's like when you are standing. It's like EV charging is like EV charging and EV fast charging, DC fast charging. It's like let's say grid is there, or let's say distribution grid is there, and suddenly you start a number of EV charging or maybe DC fast charging at very high power level. So it's like you are standing. Okay, you are standing and somebody just pushed you. Just somebody slowly pushed you. You will not fall down. But let's say somebody is the push is large enough that you cannot sustain and you will fall down, right? So here grid also, if grid stability, it is not that easy to make grid unstable. But yes, the thing is there will be disturbances in the grid, and also when there is a fast charging or amount of fast charging power that you are going to take from the grid for a short period of time, then it's definitely there will be a problem. So why I am talking about this? Now what happens? Now EV has come. When it is mobile, when you are charging your mobile, then the amount of power that you are consuming from the grid is considerably less. But when it is EV, there are now a number of EVs are coming up, and that's why when you are consuming power from the grid, it is adding up. Adding up means multiple EVs are coming up, and the amount of power that you are consuming from the grid is also increasing. Now, after two-wheelers, we are coming up with three-wheelers, and then we are coming up with the electric four-wheelers. Four-wheelers are consuming significant amount of power from the grid when there is a number of four-wheelers or four-wheeler EVs are there. But the problem is, as I told you last day, that people won't understand whether he is driving or he or she driving an electric vehicle or whether he or she driving an IC engine based vehicle. They will always compare. If you say a person that okay, this is EV, this is having n number of advantages, and then you say that person that you have to stay for 13 hours to charge your EV, immediately that person will be uninterested. It is not going to show any interest. So what has come? Now the EV company, they have to, means EV has to be a success. So what they have done in order to do that, they come up with a solution. What is that called? That is DC fast charging, where enormous amount of power that you are delivering to the EV battery, and then battery is quick charge. Quick charge means 40 minutes, 30 minutes, 40 minutes. Even there are chargers. Okay, there are very standard companies are there which have built fast chargers which can charge your EV in 20 minutes. In 20 minutes, up to 80% SOC. So that's fine. But they are assuming that the grid is infinite
the amount of energy available in the grid is infinite and we can do anything whatever we need, but definitely it is going to affect the grid. Okay. So also we will see that for the time being the state of art is we are consuming power from distribution grid. Distribution grid is 400 volt, and the major problem in distribution grid is what? The transformer that is available in the distribution grid is already bottlenecked, and then you are increasing power consumption from the same transformer. Okay, so it is already bottlenecked, so you need to see some alternative to this. Now another thing is the motivation for using EV was what? Motivation for using EV, one is pollution, another is controllability, another is advantage of there are numerous advantages and all. Running cost is less and all. But what is the motivation behind moving towards EV, electric vehicle? What is the motivation for that? The motivation for that is the renewable energy we are harvesting, and that is in the form of electrical energy, and we are trying to use the ultimate aim is to use that renewable energy to charge your EV, not from the grid. If you are consuming that electric vehicle power from the grid, there is no point, there is no success in EV. In India, our grid is what? Our grid is mainly thermal power plant based. Okay, and now we are buying EVs and we are charging from the grid. What is the point, right? So if we are charging our EV from the microgrid, forget about how microgrid will manage. But if we are charging from, forget about microgrid, if we are charging our EV, I remember I saw one video, I think on YouTube, one person in Maharashtra, what he did is he installed solar panel, rooftop solar panel, and he is having one branded EV, and he is charging his EV from that solar PV. Then it makes sense, right? But if you are charging from the grid, it doesn't make any sense. So before I am going in depth into it, first let's understand what is charging and what is the charging rate of EV. Okay, let's say, okay, before I start with this, let me ask you one very small question. What segment of EV in India is number of EVs are most? Two-wheeler, three-wheeler, four-wheeler, which is more? Huh? Two-wheelers, okay. Huh? Three-wheelers, yes, the majority players are three-wheelers. Okay, it's a three-wheelers. It is e-rickshaws are enormous number of e-rickshaws are playing different cities. Okay. Now, what we call how we charge a battery. Okay, we should not means the battery. I always told you that battery has to be taken care. The battery maintenance is very much necessary. It is, you cannot play like anything with the battery. But when it is battery, when you are using a battery in electric vehicle, when you are running the vehicle, the load or the power consumed from the battery or current supplied by the battery is very, very random, and it is high ripple current. Okay, that is why I asked this person who are e-rickshaw owner. I asked them. Okay, I asked them that for how much duration this battery lasts long. Okay. So they said, can you imagine inverter battery that you have at your home? How many years it goes? Inverter battery? 5-6 years. Even companies are giving 4.5 years warranty. Okay, but can you imagine how much life of EV battery means this e-rickshaw battery? Can you imagine how much it is? Any idea? 1-2 year. Okay. Any idea? Yes, 15 months or even 8 months to 15 months. Okay, 8 months to 15 months. And that too, the price of those battery is 40,000. Okay, 40,000. Okay, so battery is an issue. So you have to take care of battery. So what is fast charging and what is the normal charging of a battery? Now let's say one example let's take. So a car which is having, let's say, 250 kilometer range, the typical battery kilowatt hour is 35 kilowatt hour. So battery type lithium ion, which is now state of art of battery, though there are cars, standard car, which are using metal hydride battery as well, which is also successful. Okay. So nominal voltage 350 volt, the voltage has to be increased, because if you the e-rickshaw voltage is 48 volt, but when it comes to car, it is more than 350 volt, 500 volt also, because you have to reduce the current. You have to reduce the current in order to reduce the loss, in order to reduce the size of the component. Okay. Now home charger they will give. In home charger, which is 3.5 kilowatt, though it is for home it is more, because home you can go up to, let's say, 2 kilowatt, 2.5 kilowatt or so. So you charge it 13 to 14 hours. Okay. But DC fast charging, which is not available at home, you have to go to a charging station where you have to charge your vehicle. So it is 45 kilowatt, typically 45 kilowatt, let's say, assume. Okay. So it takes 60 minutes, 1 hour. So it will go from 0% to 80%, let's say. Now if you calculate, so the ampere hour of the battery is 100 ampere hour. So 1 C is 100 ampere. So when you are charging the battery at 100 ampere, so it is 1 C. So home charging, which is 3.5 kilowatt, so here it is at 10 ampere you are charging, which is 0.1 C. Okay, which is recommended actually. For a battery it is recommended, but for the human need it is not recommended. Okay, because a person cannot wait for 13 hours. Now when you go for DC fast charging, which is 45 kilowatt, then current comes down to 130 ampere. Okay, so it becomes 1.3 C. Okay, so 130%. So it is comparable to 1 C or more than 1 C. Okay, so at this, there is no hard and fast rule that, okay, at this charging current, if you charge, then it is DC fast charging. So it is, so if it is, so here typical example is, it is 1 C or more than 1 C, we can say that it's a DC fast charging. Now when it is e-bike, so let's say the e-bike of 110 to 150 kilometer range is available, easily available nowadays. So its battery ampere hour is kilowatt hour is 3 to 4 kilowatt hour. So there are 4 series connected batteries. So nominal voltage 48 volt, but it will go till 51 or 52 volt. Okay. So home charger they will give 60 volt and 12 ampere, let's say 700 to 800 watt. So it will take 0 to 8% in 5 hours. Okay. So then you have DC fast charging, which is 3 kilowatt. It will charge in 1 hour. So here 1 C is 50 ampere, because 50 ampere hour it is coming. So here when it is home charging, then it is around 0.3 C, and when it is DC fast charging, it is 1.2 C. So you have to charge your battery when it is DC fast charging at 1 C rate or 1.2 C rate, but definitely this kind of charging is going to affect the health of the battery. The reason is, what happens when you are, even if you have experienced this with your mobile, we generally buy fast charger for our mobile, right? So what happens when you do fast charging, it charges your battery very fast. But the thing is, fast charging means what? Your current level is high. When your current level is high, there is an internal resistance of the battery. So there will be I square R loss, there will be extra heat loss, and that will give rise to extra temperature rise in the battery. That will affect the chemical of the battery, and that is how it affects the battery lifetime. Okay, so that is why this kind of charging is not recommended. It is only recommended, let's say, every time you don't do this, on emergency purpose you do. Otherwise, it is better you slow charging you do, but we don't have time, we don't have patience. What we do this kind of thing, and then we forget about, then we complain about the battery. Okay. Now what happens when there is, let's say it is 60% SOC and we want to go till 80% SOC, okay, you go for DC fast charging for smaller duration. It will take, let's say, 10 to 15 minutes or 20 minutes or 30 minutes, fine. But you are doing DC fast charging for, let's say, 1 hour to 2 hours, and repeatedly you are doing, definitely you are affecting your health of the battery. Okay. So now the focus of my research when I started working on this EV charging system, my focus was the e-rickshaw players. Okay, the problem with e-rickshaw players is, let me tell you, the EVs that we use for what? The bike that we use for going office, coming back, or going to market and all. Then car, we go to some trip or maybe some shopping or maybe to the market. So it is not that emergency, or yes, sometimes it is emergency. But for e-rickshaw, what happens? What they do, they use it for what? They use it for business purpose. So what they do is, it's emergency, that's a bread butter for them. Okay. So what they do is, every day they charge, over the night they charge it. They go for a business early in the morning and then come back evening, then again they put it on charge, and then this cycle goes on. Now the problem is, when you are doing this, after some time what happens, the battery life reduces. Okay. Now there is a term called SOC, state of charge of a battery. Now there is nothing you can measure state of charge of it. It's not a physical quantity, you cannot measure it. You have to estimate it, and it depends on so many parameters. Estimation of state of charge of a battery is a difficult task. So SOC, based on SOC, the amount of charge it is showing on the panel, there is a panel where it shows how much battery left. It might not be true, it might not be the exact SOC of the battery. So what happens, sometime it happens that he or she went for the business, okay, and in middle of the day, charge is over. Okay, what we have to do? He has to come back home and then again charge, and then half of the day is gone, business is gone. Okay. So what I thought of, like, why we cannot have the solar chargers, or why we cannot have the charging stations for them, and quick charging station, fast charging station for them. Okay. So let's see what is the state of art for their battery. So they have lead acid battery. This is the first thing. They have the lead acid battery. Definitely lifetime is less. Okay. Lithium ion battery they cannot accommodate, because this price itself is 40,000. When they are giving old battery, they will get 10 to 11,000, and then 30,000 they have to pay in the span of 1 year. You see, they are doing business, and after 1 year they have to replace, 1 year or 15 months. They have to replace the battery at the price of 30,000 or 40,000. Okay. So it's a problem for them. Okay. Now that is why other companies, okay, these companies has come up with some charging techniques where they can charge at rapid charging station, but these are grid connected. These are not solar chargers, these are grid connected chargers. Okay. Now in Bangladesh there are so many e-rickshaws. Okay. Bangladesh government, what they did is, they installed solar panels at different locations, and then they are charging station. They made charging station and they can charge there. But the problem is, night time it is not available, and also it is not predictable. The solar power is not that predict. I will show you. I have experimental results and setup that I will show you how it has affected in our case. There are other chargers also, and hybrid chargers are also, which are grid connected charger. Finally we are loading the grid. Now slow charging of EV e-rickshaw results in range anxiety. Okay, definitely forget about us. For them it is like we will lose the business next day. So unavailability of sufficient public charger. Now it is not available. Public chargers are not that infrastructure yet to come. Okay. Now what happens? This kind of another thing is, if you have, let's say, solar off-grid chargers, what will happen? So even, let's say, a person is not having electricity at his home, or it is not that reliable. So what he can do is, he can buy the e-rickshaw, and he can rely on whatever charging option available outside. It does not need that he must be having a good electric supply at his home. So it is DC fast charging has refueling experience, definitely, but DC fast charging of deep discharge batteries, because if it is a battery is deeply discharged, okay, then what will happen? It will take much time in order to recharge it. Okay, so that is not good for your battery. So this is one of the very important point, that regular DC fast charging is harmful for your battery. suggested not to use on regular basis, and not for deep discharge battery where your battery takes much time. You can do it when it is emergency, you can do it. For smaller duration, recommended for smaller duration to boost the SOC. Okay. So DC fast charging is DC fast charging that an EV owner needs. DC fast charging grid doesn't need. Grid doesn't allow. Not allow. Grid will give you, because in India we have now all the, previously it was 5 regions. Now all the grids are connected together and we have one grid. Okay, one nation, one grid. 2013, it is one nation, one grid. So grid has sufficient inertia to cater this kind of thing. But in future, this is more and more coming. I will show you how the EV load is increasing. Okay, this is called top-up charging, that I told you that you don't go for full charging, you go for smaller duration charging, so that your SOC doesn't affect much. Intermittent or top-up charging, DC fast charging recommended for smaller duration and boost battery SOC, top-up driving, so that driving range you can achieve. Okay. Full charge of discharge battery can be done on emergency basis. Okay, now grid connected EV chargers. Grid connected EV chargers. So first let me explain about this EV charging thing, how it is affecting grid, then we'll come to microgrid. Now here you can see there are different kind of solutions are provided. Okay, so already I told, I think yesterday or in the collaboration meet we had, we said that we power electronics engineers now we are trying for compact solution, not for large heavy solution. Okay, so if you see here, the first case, there are 2 solutions. One is low frequency transformer base, which is 50 Hz transformer base, which will be bulky and heavy, and then we have high frequency transformer base, which is on this side. Okay, so what we do is, here what happens, this transformer is necessary for battery charging for 2 reasons. One is for voltage matching, another one is isolation, is for isolation purpose. So here also you see here the transformer is there, and this transformer is necessary for that same purpose, but since it is a high frequency transformer, its size is comparatively much less, at least 10 times less compared to the previous case for same power level. Okay. Now in second case, what it does is, now as I told you, now companies are coming up with high DC fast charging with high power level. Okay, to deliver high power, you need multiple such solution connected in parallel, because voltage level we can achieve 300, 500 volt we can achieve, it's not a problem. But in order to achieve the current level, it is only possible when you use parallel connection, or parallelly the converters are connected in parallel. The 2 things that you can achieve, reliability will improve, because if one converter goes down, then you can play with the other converters. Now this is typical, there is no hard and fast definition yet arrived, but typically this is level 1, level 2 and level 3 charging. Okay, level 1 up to 2 kilowatt, and then because level 1 is mostly home chargers. Okay, if it is home charger, then you should limit, you cannot go for very high power level, because at home it is current level is limited, and when it is level 2 and level 3, it is power level is high. Okay, power level is comparatively high. Now you can see DC fast charging, it is 0.24 megawatt. Okay, 0.24 megawatt, and that too for only EV charging and from the distribution grid. That is the main point. It is from the distribution grid that we are taking. Okay. Okay, now let's see. So how the EV charging current scenario is uncoordinated charging. Uncoordinated charging means there is a team working on something, and there is no coordination between them. Okay, it might happen that somebody is doing one work, another one is doing same work, and the work, that same work is means it is repetition of work. Okay, there is no coordination, there is nothing. So here also you can see here, when there is an uncoordinated charging scheme, where because we are not thinking, we are thinking that till now we are very calm and cool, because the EV charging is not reached to that level. Okay, we are thinking that grid is a pool of power. It's a huge pool of power. It's like a sea, and we are taking one bucket of water. It's not a problem for the grid, and that's why the uncoordinated charging scheme works well. But actually, in future, it will not do. Okay, so what is happening here? So EV charging station is there. Then there is a grid, and there is a renewable energy sources. Okay, so renewable energy sources, whether it is there or not there, okay, grid is there. We are very, very sure that grid is there. Grid will take care of it. Whatever deficit is there, grid will take from the grid. It is like you have sufficient money in the bank, so you are spending. If some other source is also giving you money, if that source is not there, I will take from the bank. But this will not do, because you have to go for alternative. Also, it is since I already at the very beginning I said that grid is coal based, thermal power plant based grid. So we are not recommending that EV charging power you take from the grid. So here you can see that during this period, when already grid power is in peak, the EV power is also coming at that same time. Why not to distribute it? Why not to distribute over the 24 hours? This is 24 hours. Over the 24 hours, why we are matching EV charging peak with the grid charging peak? Then it's a problem for the grid, right? Grid margin is definitely there, but after that what will happen? So what are the difficulties that we are going to have here is, so voltage stability, frequency stability, rotor angle stability, different grid stability issues will come into picture, because there will be a demand response mismatch will be there, and grid has to, we don't know, it's EV randomly comes and somebody start asking, like that is why this AI, we talk about AI, right? Now what people are doing now, like they charge scheduling they are doing using AI. Okay, when you go to a charging station, now the AI will tell you whether your EV battery is suitable for level 2 or level 3. If it is not suitable for level 3, then they automatically will move to level 2. It will check the grid quality, whether it is suitable for level 2, level 3. Accordingly, they will set. So somebody is taking care of it. That means somebody is coordinating. Okay, that is necessary in order to save our grid. Okay, now another thing comes into picture nowadays, but it is very difficult task. There is a concept called, one is vehicle to grid concept. Have you heard of it? Vehicle to grid, vehicle to building, vehicle to grid. This concept is coming up. Okay, so here I remember in one movie, this I think 3 Idiots. This Amir Khan was telling that he is making an inverter. That inverter will take. He is proposing that in wedding ceremony there is a power cut. So what to do? We'll put an inverter, we'll use the car batteries to power up. The nice idea, right? But the thing is, car battery has to be used, right? Now here also the concept is the car will supply power to the grid, right? That's fine. The grid is more than happy. I am getting power from somewhere. I have given it the power to the battery at some time. Now I am having deficit. It is giving power. But if you are an EV owner, you will not allow this. Why? Because your battery is engaged throughout the day. Your battery is working. Your battery is charging. When you are driving, battery is discharging. When the car is not doing anything, it is connected to the grid. There is a power exchange. So in that sense, what will happen? The battery health is deteriorating. Okay, the owner may not allow this. So vehicle to grid is a technique, but owner may not agree with this. Okay, let's say there is a charging station. So you are going in a long journey, and there is in the highway there is a charging station where you put your car, and then you will be there for, let's say, 1 hour. Now it might happen that your car battery is charging and also maybe discharging when vehicle to grid mode is activated, and it is helping the grid. But the owner must agree with this, that okay, I will allow this. Okay, Now there is a coordinated charging scheme. So there is a supervisor here, you can see here there is a system operator which will supervise. So sources are there, so grid is there, renewable energy source is also there, and there is a charging station and EVs are there. The extra thing that comes into picture is the supervisory part, which is a system operator which will schedule, as I told you, that it will schedule, it will monitor, it will see whether which one is available and all, and that is what the management that it is going to do. So there will be a communication which will get to know, because it has to know the system condition, and then this coordinated charging is going to give this kind of charging profile, where you are shifting your peak from this to you are increasing of peak grid period, you are charging, you are increasing. This effort can be done in order to increase the in order to stress out, in order to release the grid from EV charging stress. Okay, this effort has to be there. Okay, so charging large number of EVs cause substantial stress on the distribution grid. Okay, so it is distribution grid, EVs are increasing, so it is putting stress on the grid. Load curve moves outward, increase the load on the transformer as well. So heating will be there. So intelligent and effective management should be there. Okay, now uncoordinated charging will not do. Even if it is a microgrid, we'll see. Okay, grid requirement and negative effect of charging on grid needs to be considered. Okay, and uncoordinated charging on the, such as uncoordinated charging on the distribution grid. So it is not recommended. So what happens? So you can now integrate more renewable energy. Okay, more renewable energy. But the problem with renewable energy, let's say wind power, you must be knowing what is the problem with wind power. One is intermittency, or maybe you cannot predict. But what is the another issue that we have with wind power? If anybody can tell me. Huh? All are AC power. You are connecting to the grid. But one major issue is there. What is that?
Location and size.
Size is okay. It is installed. It is generating power. Okay. The problem is, let's say grid is not in a position to take power. What will you do? That power. Right? You are not in a position, whatever power is generated, you have to waste the power. You have to connect register and you have to waste that power. Or you have to install storage. There you store the power and then later on you can use it. Storage term is very easy to say, but electrical power storage is not that easy. It's a costly affair. Okay, you have maintenance along with it. Okay, because storage, we understand storage means what? Battery. Currently what we have is battery. So vehicle to grid technology can mitigate the issue of help improving efficiency and stability of the grid reliability. Okay, regulates power. So that's, but vehicle to grid technology cause deep discharging. Okay, battery degradation, battery life, and decrease customer satisfaction. So customer may not allow with this. May not allow for vehicle to grid charging. So use of intelligent strategies like AI you can implement. People are working on it. How to use AI for charge scheduling and all, and in order to make these things more efficient and reliable. So also coordinated charging you can do. Okay. Now if we come to microgrid, so the very first question that I might ask you, why there is a need for microgrid? Why not renewable energy that you use for charging? Why we need a microgrid though? Okay, the thing is, microgrid, it's a grid. It's a grid. Grid means whether it is micro, nano, whatever it is. If it is a grid, that means what? The grid is having a specific voltage level. The grid is having some bus. That bus will have some specific, you are going to maintain that voltage level. Okay, so this is the difference. So when it is a microgrid, you are defining the grid voltage. It could be hybrid microgrid, it could be AC microgrid, it could be DC microgrid, whatever it is, you are going to maintain the grid voltage. That makes sense, because what happens here, if you can see here, let's say DC microgrid. Okay, so what happens? you have power grid. You see, we are still relying on power grid. Even if it is a microgrid, we have to connect to the microgrid. The reason I will tell you. So here are the sources that we have. PV system we have, energy storage. This is must. Without energy storage, it's not feasible at all. Energy storage or grid connection must be there. Otherwise, there is actually what will happen. So wind and PV system, it will keep on generating. Okay, keep on generating. Sometime it will be more, sometime it will be less. So that buffer power, from where it will come? Either you take from the battery or from the grid. If grid is not there, the battery plays the crucial role in communicating that power and maintain the DC bus voltage. Okay, so if it is, so in this DC microgrid, if this is the DC bus, the battery which can maintain the DC bus voltage. No other. So power, this grid also can maintain, this utility grid also can maintain the DC bus voltage. But if this DC bus voltage is not there, the grid is not there, it is the battery along with some, it could be some HESS also, hybrid energy storage also you can use to maintain the DC bus voltage. Because in order to maintain the DC bus voltage, let's say when power is more, so what will happen? The DC bus voltage will go up. If power is less, the DC bus voltage will go down. So the battery should take the power, battery should communicate this power. That means power exchange should be there from the battery to the grid. Now, as I was mentioning, why the grid has to be maintained, in microgrid, what is the benefit that you are going to get when the grid voltage is maintained? The advantage that you are going to get is, I told you yesterday, whether it is wind, whether it is PV, whether it is mini hydro, whether it is fuel cell, you need MPPT to be tracked. MPPT, maximum power point, to be tracked. Maximum power point tracking can be done, let's say PV system, this DC-DC converter. But the first criteria that you must have is, this side voltage has to be maintained. Then only it is easiest way to do the MPPT. Okay, so this side voltage, if this side voltage is not maintained, it becomes very difficult, and sometimes you may not go for MPPT, you may not achieve MPPT. Similar for wind system, similar for other system as well, other distributed energy system if you have, then it's a similar thing is here. Only thing is it is AC bus. So there is a comparison between DC microgrid, AC microgrid, the number of converters and so forth. And there are hybrid microgrid as well, where we have both AC bus, DC bus, everything is there. Okay, but here you can see here that there are electric vehicles that you can charge from the DC, from the microgrid. Now, if it is here, it is mentioned that fast charging. So fast charging means the EV owner won't understand whether your microgrid able to supply or not. He will come and will ask for, let's say, 240 kilowatt charging, right? So your grid must be sufficient enough to cater. If you are saying, a microgrid is saying, yes, I will supply for DC fast charging, the microgrid should have that reserve. That microgrid should have that reserve. So in order to, okay, let's see. Okay, so microgrid, on grid or off grid, generates electricity using distributed generation on demand. It's a very reliable. When there is a demand, it will generate according to demand, and it generates locally. There is no transmission. There is no. That's the benefit of use of microgrid. That is, whatever you want, you are generating locally. There is no transmission, and this local generation is mostly, or 90% case, it is renewable energy. Okay. So it is taking care of the EV loads, mainly EV loads, since we are talking about microgrid for EV charging. So if it is taking care of EV load, so grid is, the stress on the grid we are reducing. So grid flexibility we are improving. So it has both generation, it is generating also and supplying also. So it's a grid, it is having both generation and load. So in the era of EV charging, it helps EV user to provide an alternate option to charge and reduce the peak demand. So the peak, as I was showing, that peak, the EV peak which was coming during the night time can be shifted, and people can charge. Now there are other like as I was mentioning, like AI can be utilized for charge scheduling. Let me give you one example. One example I already told you that based on your the grid quality, quality or based on your battery quality, it will automatically will tell you whether you should go for level 2 or level 3 charging. That's fine. Now another thing is, let's say it will tell you, so let's say one location, there are different charging locations. At one location there is a crowd and people are already doing let's say DC fast charging. So that location grid is already stressed. It will tell you, you don't go here, it will en route to some other location, maybe far away, maybe little bit far away from whatever is the near location. Why user will go to the far location? Because now it will give you the cost benefit as well. It will tell you that okay, if you go to this charging location, it is crowded and here the price is more. If you go to other location, the price is less, but you have to go little bit far. Okay. Similarly, here also, now in grid also, utility grid, what they are saying that if you are taking power during this period, I will charge more. So better you move your charging to some other time, so that your cost is reduced and also grid will be stress free. So like that they are trying to reduce the stress on the grid during peak hours. That is why I remember one of my friend was telling in other countries what people are doing. They are washing their clothes. They are using washing machine at night, so that the so that their cost becomes less. Some country this cost is water cost, electricity cost is much higher. Okay. So it's a dynamic energy management with distributed system, and it's a sustainable power grid. As I was telling, it's a grid actually. When you are saying microgrid, if somebody comes and tell you this is my microgrid, the first and foremost thing is whether you have to check whether that grid is maintained, that voltage whatever they are saying, whether it is maintained, and that maintenance of the grid with fluctuation in load or connection or disconnection of the load or generator, it is maintained or not. That is the first thing that then only you can say it's a grid. Okay. And there are different control strategy. This I will tell you tomorrow, because tomorrow there is hierarchical control I will explain. There I will explain these things. So this I already told you, that the critical issue of why microgrid, why not just directly go to renewable energy and charge. That will do, but charging station won't do. So critical issue of power generation with renewable energy, it's a variable, discontinuous and poor predictability. So hence poor reliability and power quality. So power quality is a big term. Sometimes if somebody asks, power quality means we understand the TSD of the current, TSD of the voltage. It is not like that. Power quality is how much voltage level that you have at your home. Let's say you have single phase supply, you should have 230 volt. You are getting 200 volt. Then it's an issue with the power quality of that utility supplier. The power during daytime, there are n number of times the power is not available. Then it's an issue with the power quality. Okay, it is not always the current quality or voltage quality or TSD that gives to power quality. Power quality means all these things comes into picture. So it's a development of self-sufficient grid. It could be micro, nano, whatever it is based on your requirement. Okay. Now, far and foremost component of a microgrid is battery energy storage system, which is going to maintain your, for let's say for a DC microgrid, it is the battery energy storage system which is going to maintain your DC bus. Okay. Now what happens, it's as I told you, it's a costly, right? It's a battery energy storage is costly, maintenance is there, you have to replace it. It works as a buffer. I understand, it works as a buffer, it consumes, it releases power. But thing that you need to keep in mind that it has to be, this lifetime of this battery has to be increased so that utilization of this battery energy storage should be optimized. Now, how it can be done? If you optimize the EV load and the power exchange between the microgrid and the EV, right? Sorry. So, if you can optimize the load on the microgrid, which is that power exchange between the vehicle and the grid and the amount of power that you can optimize, then you can optimize the life of this battery energy storage. I am particularly specifying this battery energy storage system because this is one of the vulnerable or one of the cost component, that is why it has to be taken care. So, for EV charging load, power exchange from EV to microgrid has to be optimized. So, I think madam already has discussed about energy management system. So, there are numerous energy management systems are there for microgrid. So, you should have a robust energy management system which can manage the power exchange by the sources which are generating power to the microgrid, and also the consumption by the load, so that you can optimize the power exchange from the microgrid to the sources and to the load as well, so that microgrid becomes reliable, the stability improves, and hence you can rely that yes, I can come with my e-bike and can charge. I'm sorry. Now, so EVs can be, so for energy management system, we can treat for implementing energy management system, it is up to you that how you are treating the electric vehicle. Actually, electric vehicle is nothing but a battery. Okay, so this battery you can treat as a whole or you can battery individually. That's up to you how you are going to implement the energy management system. So, what we need a robust energy management system. This I will discuss tomorrow, how this control of microgrid can help. Okay. EMS is supported by real-time monitoring, that is very much necessary because there is continuous generation, there is a continuous load consumption, so it is very much necessary. So, there must be a monitoring of the system with real-time data and collects all the information about generated power and consumed power. Power buffer BSS is a must, which enable compensation. This is what I was talking about. So, EMS needs accurate SOC estimation because battery energy storage system, it's based on SOC, okay, and needs appropriate communication system. That is very much necessary, as we have seen in coordinated EV charging system. And this bidirectional, as I was talking about, though for the time sake, if we assume that yes, owner will allow us to for vehicle to grid power communication, then it could help. So, EV bidirectional charging infrastructure charging as well as V2 microgrid power exchange services can significantly improve the reliability of microgrid. Okay. Now, as I was talking about this e-rickshaw player. So, we have done one work, has done one project with the IIIT Hyderabad. There we have developed one system where we are charging electric vehicle. Here we have taken battery, where we are charging using solar power and that battery energy storage system, and we are trying to charge electric vehicle. It's a standalone system that will show you. So, what is the role of battery? Let me just explain this. This will be very useful. So, EV battery is taking power like this, and there is a battery energy storage system which will give the ripple power, and the average power will be taken from the solar PV. As I told you, solar cannot give this. It is better, in order to improve the lifetime of solar, better not to take ripple power from it. So, that is why this battery energy storage also. This battery energy storage system will act as a buffer. During night time also it can supply power. Okay. So, this is what we started with, the hardware we started with. So, here it is a triple port converter. It's a triple port converter. So, there are 3 ports and we have 3 bridges. So, first we in the laboratory we tested it, how it is working or not. So, here we can see that these are the batteries. So, 2 battery here and 1 battery here, EV battery and battery energy storage system, and this is high frequency transformer based solution. High frequency, this is high frequency transformer. Okay. So, that is why we use a high frequency 3 winding transformer that we have used here, and there is a port 1 where EV is this PV is connected, and this is EV battery and this is BESS. With this we obtain few results. So, battery current, and here we have battery current and battery energy storage system current, and with the inductor current on the primary side. So we have tested first, we have tested it on the laboratory test bench, and then we have developed this. Okay, it started with this. So this is the core power converter. Yesterday, if you remember, we have made a block diagram where we have told that the power processing unit, this is the main heart of the power conversion system. So here we have this power converter we have developed. There are 3 edge bridges, and we have this 3 winding transformer, and this is the DSP microcontroller, and this is the inductor. And then we have used it in the outside using we implemented outside, and we have tested using solar panels. So we'll tell you how the solar panel is affecting us. So it is this setup we have tested at 11 a.m. 11 to 1 a.m. Okay, so that time the solar was at peak. Okay, but still I will show you what is the problem. So if you see here, this is the temperature of the solar panel, 52 degrees centigrade. Okay, and we had five panels of 50 watt each. So we suppose 50 watt power, peak power. Supposed to get to 50 watt, we were getting only 102 watt. Slightly more, we got 110 watt. Okay, so at this temperature level, so we had 6 panels. We supposed to get 300 watt, but because of rise in temperature, we only were getting 100 watt. We tested with that also, and we got the result of EV charging, the battery, not EV. The battery we have charged. So here the batteries are there. Achha, here we cannot see. This is a trolley. Okay, this is a trolley. Here we put all the batteries, and here is the converter, and then solar panels are there. So we have designed in such a way that it's a movable thing. We can move here and there, and then we can use it for charging. Now we are more testing we are performing on it, and we are planning to install it in some parking location. We have seen that there are many two-wheelers are coming, people are using. We'll request if they allow, we can test with the two-wheelers also. Okay, so this is what we have. So EV charging is one of the most demanding and unpredictable load on distribution grid. This is unpredictable. Somebody will come and play. Unpredictable load is your mobile charger also, but the mobile charging power is much less. Here the power level is much higher. So if it is going to the grid, the several EVs are coming and playing, is connected to the grid, then it's a load to the grid. It's a random load to the grid. So it has detrimental effect on the distribution grid. Okay. Now EV charging from microgrid reduces stress on the grid substantially. Definitely, the grid says that okay, you have another option to charge, you go and charge. But microgrid has to have a robust energy management system in order to cater this EV load. Okay. Okay, so few references I mentioned here. Okay, so I'll stop here. Thank you. So if you have any questions, let me know. So online, offline participants, if you have any query, let me know. Otherwise, we can close the session. Okay then. So if no queries are there, okay, so I must thank you for your patience and for listening to this lecture for last 1 hour. Okay, thank you.
Sir.
Yes.
Sir, I have one question. Sir, how can we improve the charging? Because charging is the main thing. And fast charging is one of the main concern for the EV. So if we can do fast charging, also batteries should not get deterioration. So this is the main concern in the industry, that how can we charge fastly as well as battery should not, reduce its life. What could be the main research in these things?
Yes.
To elaborate.
So fast charging is affecting what is the current state of art of our battery. People are working like anything on battery technology as well. So I heard of, I don't know much technical about, sodium batteries are coming up. Okay, people are working on it. So I don't know whether it will be suitable for sodium batteries. It may not be, means if it is always, if it is an EV if it is for EV application, that's what I always tell, that it is application specific. Lead acid batteries are not suitable for EV. Okay, lead acid batteries are suitable for home inverters, fine. Lithium ion batteries are suitable, metal hydride batteries are suitable for EV. Similarly, what I am thinking, like in future, whatever current state of art, it's affecting our battery when it is DC fast charging. In future, it might happen that there will be technology and battery technology will come up which can cater. Definitely, it will affect those batteries also. But even then, we can find that, okay, because of with fast charging also, the battery life is not affecting that much. So in that case, it will be suitable. But definitely, with the current battery technology, whatever you have, that is, your battery will be affected. That is what I can say. You can use it, but battery will be definitely affected because of the very, very, very basic reason that there will be an internal resistance and there will be losses which will heat up your battery. Heating of a battery is not good sign for battery health.
Thank you, sir. One more question, sir. Vehicle to grid is basically a software concern. So, what are the, I mean, in the next session or coming session, I would like to know about how we can communicate from vehicle to grid, some basics ideas regarding what are the grid codes and what are the protocols. So, because this is important. Main thing is these are the basic concepts, but what are the grid code and what is the technology that we are using rightly to communicate from vehicle to grid or grid to vehicle? Because many companies like Schneider and ABPs are working, but what are the grid codes and also so that we can deeply involve in these things?
This bidirectional vehicle to grid technology is still in research. I don't think industries are working on unidirectional chargers. They have not, means the commercially available chargers are till now, in my knowledge, it is unidirectional in nature, because mainly if it is a two-wheeler, they are using this PSFB. So there the output side it is diode bridge rectifier. But when you want this charger to be bidirectional, then it has to be a DAB converter based or any other converter which is bidirectional in nature, so that the battery can supply power to the grid. But there should be certain condition, as you were telling, that grid code should be in place. So when this grid to vehicle to grid technology comes into picture, definitely people will think on this, because vehicle to grid is not, that also is not small amount of power. Okay, it will be huge amount of power that is going to inject to the grid, and that has to be in place.
Okay, sir. Thank you, sir.
Thank you. Okay, so if no questions are there, so we can stop here. Okay, thank you so much.